Ur. He received his PhD in 2009 from the University of Cambridge. And then he spent some time as a postdoc at IRIF in Paris and then at MPI in Saarbrücken. Today he's a professor at Seoul National University, where he's leading a group of people focusing on formalization using the rock-proof assistant of software used to produce and verify software. And he made an impressive amount of contribution in that field. I especially remember when he did some work on improving the semantics of pointers for the COM30 compiler. And he also was involved in other projects related to the semantics of low-level languages, to relax memory concurrency, to separate compilation, and to program logic. And today he will tell us about a new verification tool called Chris. So please.
Okay, thank you. Thank you for the introduction. And so today I will present a notion of imaginary spec. It's really similar to imaginary numbers in mathematics. So now we can say that we also have an imaginary spec similar to imaginary numbers. This power of, and I will show you the power. So using the imaginary spec, actually we can merge, inherently marry two approaches in verification, simulation relation and separation logic. So simulation relation case, usually it proves refinement between two programs. So the spec is given as abstract program, and the implementation's behavior, the I/O behavior, matches with the spec's behavior. And then used by COM30, CertiCourse, SAL4, and some verification project. Whereas the separation logic is more program logic style. So spec is given as a pre and post condition. And the goal is program does not go wrong, or basically safety guarantee. But it provides a very fancy modular reasoning principle, frame rule, and also separating conjunction, and so on. So there is a main tools based on separation logic. So using the imaginary spec, we can merge them really nicely. And also more, not just merging. We can get something new, okay? So anyway, so we can marry them. So yes, using imaginary specification. So what's the imaginary specification? First, like in the mathematics, you have real numbers, and you can extend the real numbers into imaginary numbers. So, and the power is that it may make your proof easier. For example, when you prove cosine square plus sine square is equal to 1, we know that cosine x is equal to this imaginary number representation. Then, once you turn it into imaginary numbers, you can do just a polynomial computation. Then you can get 1. So it makes your computation easier, right? So similarly, we have just a normal notion of a specification, and we can I will extend it into imaginary spec. And then it will have a similar role. So in general, we will prove that by linking many implementations together, real implementation. So this orange color is a real spec. And then I want to finally prove that some top-level real spec. And then I want to prove this refinement as an end-to-end goal. But we can decompose this proof into multiple different directions, horizontally and vertically in many ways. And then the nice thing is that in the middle, if we use imaginary spec, we can decompose this proof. So even using the imaginary spec, this in the middle spec can subsume all iris style, iris separation logic predicates and simulation style, all kinds of operation, I/O, everything can be specified in the imaginary spec. So, so that's the goal. And okay, so first, let me tell you the definition of imaginary spec, which is not very complex. First, the real specification, I would say, basically operational semantics with natural operations, natural non-determinism, so which people call demonic non-determinism, but I think in this context, I will call real non-determinism. And so the real choice is, for example, if you choose X, choose from the set X, then you get possible values, and then you do continuation, right? And then the behavior of this program is the union of behavior of each continuation for each value, each chosen value, right? So that's a usual kind of operational semantics, and this is kind of how usual machine in real world works. It can make some kind of choice, non-deterministic choice, and then it performs. But imaginary spec has something else, some different mechanism, which is people call angelic non-determinism, but in my context, I will call imaginary non-determinism because the purpose is different. And here, so I call take x. So this is also non-deterministic choice. Take x, and then you have a continuation for each value. But its behavior is intersection of each continuation's behavior, not union. It's a duality, right? So, and then there is no such machine. It's hard to implement such a machine in real world. But anyway, so let me give an example. For example, this program only having real non-determinism, real spec. So you choose from 1 and 2, and then print C. Then its behavior, possible behavior is a set, print 1 or print 2. Two possible behaviors, right? And then 2 and 3, then you have print 2 or print 3, right? You have two possible behavior. But now I will use imaginary spec. For example, you take from true and false, imaginary way, and then if B is true, I perform this first program, otherwise second program. Then the behavior of this program is just printing 2, because only print 2 occurs in both branch. Print 1 occurs only in one branch, so it's ignored. So this is the semantics of imaginary spec. So this is imaginary because it's hard to implement this kind of machine in real world, because in order to print 1 here, you have to know that all the other branches, all execution you have to know. So it's a kind of basically a halting problem, even harder than halting problem. So it's kind of impossible to implement and there is no such machine in real world. But in the imagination, we can think of such a machine. We can mathematically define and then use it to specify things, okay? So now I will give you some nice example which motivate this imaginary spec. So this is a simple program. Let me first explain. Okay. So this module cell has a local storage, only accessible by the functions in this module. Let's call it current value. And then set function is simple. Just invoke some unknown function input. The input function may get input from the user and then return it, or maybe do something else. But anyway, this is an unknown function corresponding to input conceptually. And then you store the value into CV. So set function changes the current value, but via this input function. And then get function just return the CV. So this is some simple, silly library. And then the main function may use this library. So cell.set. So cell.set just set the value, but via input function. And then foo.foo, another unknown function you invoke. And then you invoke cell.get, and you get value and then print y. So this is some simple program. Okay. And then so in this case, if you know that foo.foo does not invoke set in the middle in this point, for example, so in other words, if foo.foo does not interfere in my execution, then I can abstract this program into this program. So here, just so you eliminated the invocation to set function and get function, just to directly invoke this input function, and then invoke foo.foo, and then print y. So this program and this program's behavior may be different if foo.foo interfere in the middle, right? Because this code is directly print the value you receive. So even if foo.foo invoke set function, the value, the printed value will be the value you received, the first value you received. But here it will be different because foo.foo can change the value, so the value you print may be different from this one, right? So I want to verify this one, assuming that foo.foo does not invoke cell.set, okay? But in a very, very extremely modular way, okay? So then, first what you have to do is we have to verify this cell library separately, completely separately, independent from the user code, right? Okay, then let's verify this cell module. Okay, set and get function. What would be the spec of this set and get? So natural separation logic spec, one try might be something like this. So this cell X is in separation logic some kind of a resource predicate, and then it can be as kind of points to predicate, and it represents the internal state of the module. So cell X, if you have a cell X resource, it means that the cell module has a X value in the current value storage. So if you first, as a precondition, you get cell X, and then if you invoke get, then it's guaranteed that the return value must be the same, the return value must be this X. And then still cell X remains because the get doesn't change the state, right? And then, but set function is problematic here. So okay, I give you cell X. I know that X is there, but what's the post condition? What value do I get? I know that it can be changed, but what do I get? So maybe currently naive approach would be just exist Y, cell Y. This is sound spec, but is it sufficient spec? Can I prove the previous example using this spec? I cannot, because you lost the information that the y is the value given from the input function, right? Okay, so then how can I specify? So I can specify in this way using imaginary spec. So the idea of imaginary spec is arbitrarily mix operational semantics, just the operation and then separation logic assertion. So separation assertion, two kinds of assertion, assume and guarantee, and then and arbitrary code can be mixed and they can depend on each other. So that's imaginary spec. So I can encode this notion of mixing condition and operational semantics in an arbitrary way using the imaginary non-determinism. I will show you. So here, so let's read this spec. So it says that first, take some value x, which corresponds to this x. But this x is not given from the user, because if you get the function, it has no argument. So actually, caller of this module would not give you any value. But this is x is taken in your imagination. You just non-deterministically choose x. Like just you imagine that this value is given from the user, but actually it's not given from the user, but you can imagine that. Okay, so some non-deterministic choice. And then you assume that cell x would hold. It's also in your imagination. You don't know anything about other modules, just in your imagination, you assume. And then you invoke input function and you get y. And then you guarantee that kind of condition, it's a cell y, not exist y, cell y. It's a cell y, exactly the y is given from the return value from input. Okay. So exactly the value comes from. So this spec exactly specify that the cell y, the y comes from the input function, result of input function, okay? So that's our imaginary spec for this function. And then the get function, the imaginary spec would be basically same as the separation logic spec. Like this part is a precondition. You take x at x, and then this is postcondition. I guarantee cell x and return x, okay? So, and then this can be actually proven in our tool, and also it's a contextually, this refinement hold contextually. It means that for any, you link these two programs with any arbitrary imaginary spec, including real spec, the behavior is refined. Okay, so that it holds because of the interesting encoding of this assume and guarantee. So that guarantees that kind of thing. And here, encoding is quite simple, and then we can just tell you the encoding, but just briefly because the mechanism is quite simple. So somehow understanding may take time, but for now, just assume that this A does something interesting, but just I will tell you the definition. So given this P is iris prop, and this P is a mathematical proposition. So assume P simply means that if P doesn't hold, take from empty set, which means it's a undefined behavior. So it triggers passive behaviors. Okay, it's a top set. Okay, full set. And then guarantee P is if P doesn't hold, choose empty means that it's empty behavior. So if choose false means just the execution disappears. Okay, and then now I can encode the assume over this iris proposition. And then here, the only thing is that we have a global resource where some resource is stored. We have a repository for storing single resource. Okay, so that's a get RES, and so this get RES is a reading from the repository. Put RES is putting new resource. Okay, so that's the only thing, special thing. And then also this get RES and put RES is only accessible via this assume and guarantee. So using interaction tree, we can prevent. There's no way to access this one. This is the only way to access it. So we know that how it's controlled. Okay. So get RES. First, you get some resource from it, and then you, in your imagination, you take new resource which will be put it back. Okay, MR prime. And then assume that what you have chosen is valid, and then so you assume that the MR, the newly chosen one, implies the P and the original one. It means that the new one contains both existing one and then new resource that satisfies given P. So somehow assume P, after assume P, you have more resource, right? And then you put the resource back. And then if you think of this semantics of take, any resource that does not satisfy these two will trigger UB. And then the total set UB is identity to intersection. So the behavior you can just ignore. So the actual behavior of this one is the intersection of MR prime that satisfies this one, okay? And I will not exhaust. So get RES and then choose new one, and then prove the duality. So it means that this one is, the new one is existing one minus P. So existing one should imply the P and then the new one. So new one is conceptually, you take away the P, okay? So that's all. Okay, this is perfect operational semantics, and it has a proper notion of set of behaviors, IO behaviors, and so on. Okay, so now, using this spec, I can verify this main function. So this refinement does not hold in general. I have to know what the spec of cell get and set get, right? So if this is arbitrary function, this refinement cannot hold, right? So I need the spec. So in this case, I will only use this spec, the gray part, right? So in the verification, when I use this spec, I link the source program and target program both to the spec, and then prove refinement between this linked program and this linked program. And then the reasoning principle for using this spec, that's something completely new in our CRIS work. So we have earlier work, but that didn't support this kind of idea of mixing condition and operation arbitrarily. But here it's possible, and then when I use this one, essentially reasoning principle is just inlining. When I invoke this one, I jump to here and execute it and come back. So I can just treat this code plus conditions as if it's my own, just code. I can just execute it like as if it's my own code. So when I invoke cell.set, I just execute it. So that's all. That's the reasoning principle. So then this spec in an intended way. So okay, let me show you in detail. So first, this source program does not invoke any of a cell function, so I just hide it to make some space, okay? And then I will show you how this proof works in iris proof mode, okay? So first, it's a simulation relation, so we start with the same place, and then in our simulation relation, we can take a source and target separately. We don't need to take both steps at the same time. This is thanks to the FreeSim work, so we use that idea. So, and then what I do is that first, I execute this assume cell 0. Then what happens is that I obtain this cell 0 resource in iris proof mode hypothesis, okay? So I obtain this one. And then I execute this target side, so cell.set. So by inlining, I can essentially jump to here. So my code goes here, and then I will keep executing it. So now I will execute take. And then take, if it occurs in the source side, it's like a really, you are taking some value in your imagination, but if it comes in the downside, the target side, it behaves dually. So it means here you can choose, instead of a value is given, you can choose. So if you execute it, actually the logic asks you to choose a value. So in this case, I will choose value 0, because otherwise my proof may not go well. So I will choose 0. Okay, and then assume cell X. If this occurs in the source, I'm given cell X like here. So this assume I was given cell 0 because it was in the source side, but this assume occurs in the target side, then it's a duality. I have to prove cell 0, right? How can I prove cell 0? Because I already have cell 0. So after this one, I proved it, and my cell 0 has gone. So in the iris proof mode, nothing. Okay, it's gone. Okay, now both programs are waiting to invoke input. So now I invoke input, even though it's completely unknown function, I can just invoke simultaneously. It's like a normal simulation relation. I can jump over it because I invoked the same function with the same argument. Okay, and then I can assume that the return value is equal. So that's the logic provide. And then, so let's say the return value is I. Okay, then both the source program and target program has value I. Okay, then I execute the target side. Then I again receive cell I, right? Because this guarantee is a dual. So now guarantee in the target side will give me cell I. So previously I had a cell 0, but after executing this set, now I have a cell I. Okay, so I return. Okay, now both programs are about to invoke foo-da-foo, which is a completely unknown function, but our logic allows to, if they invoke same function with the same argument, then it's okay. You can jump over it. Okay, and then now the target program also cell.get. I will execute cell.get. Okay. Here, so another important point is that actually foo-da-foo can interfere you in real world, but in the logic we can assume that foo-da-foo does not interfere. So that's the power of separation logic. Since I own cell I, the foo-da-foo does not own cell I, right? So foo-da-foo cannot invoke cell.set because the cell.set has require as a precondition this cell resource, but I have a cell resource, so no one else can have a cell resource. This is cell is unique in the separation logic resource. So somehow logically I can assume that I can reason locally without worrying about foo-da-foo. But in reality, foo-da-foo can invoke it. So that's the power of imaginary spec. So this encoding of take and assume can make sure that if the foo invokes cell set, somehow it triggers UB. So this program trigger UB, so source program trigger UB means that arbitrary behavior can happen. So refinement just trivially holds. So that case is covered by our encoding. But in the logic, you can assume that foo does not interfere with you. That's your intention of this resource. Okay. Okay. Just a second. Okay. Cell.get. Okay. I jump to this one. And then now I take int, so I can choose one. So this time I will choose I, okay? And then I have to I have to provide the cell I, right? But I have a cell I, so cell I is gone, empty. And then I get cell I back because of guarantee. And then I return I, because this value x, I chose I, so I know that the return value is I, right? Return I. So here, I know that this y is I, right? So both this one is I, this one is I. So I print at the same time with I. So it's guaranteed that I print same value. So the refinement holds. So this is how this refinement works in our proof mode. I will give a demo in a minute, but okay, that's all. And then now we had two local reasoning about. One is about this module cell, and another is about main function. And I will show you how to compose them together. So first, this one I haven't shown you how to prove it, but it's a very easy proof. But anyway, assuming that we prove this one. And then since this is a contextual refinement, we can compose with this main function implementation, okay? And then this main function with the spec, we just prove that this one refines the main spec linked with the cells spec, right? And then by transitivity of contextual refinement, we can get this one, okay? And then, since this is also contextual refinement, I can add arbitrary identical context, which is foo, okay? So this refinement holds. So it means that this holds even when foo interfere you. So if foo does not invoke set, somehow intuitively we know that this refinement holds. But if foo invokes cell.set, then we know that intuitively this one will print first value, this one will print the second value. So it may be different, right? And the only way it's possible this holds is because if foo invokes cell.set, some UB will happen, undefined behavior will happen, right? So I will just check. Actually, that's the case. And then this is not the case in the previous work. CCR, this refinement does not hold, but now new quiz, this holds. Okay, so this was our previous encoding, and I will just briefly tell you why UB happens. So for example, here at the beginning, so let's execute the only source program, and then I will show you UB happens if foo invokes cell.set, okay? So, and let me execute this assume. So then first, the cell 0 is given as argument, right? And then I get value from the repository. But in this program, initially it's empty, okay? And then I can take some cell 0, but actually I can take arbitrary value. But if you take other than cell 0, it's always false here because the P is cell 0, and then MR prime is something else than cell 0, cell 1, for example. Then cell 1 cannot imply cell 0, so it will be false. So you can ignore that. And the only case which survives is the cell 0. So you have cell 0, then it means that the repository now contains cell 0. You put cell 0 in the repository, okay? And then if foo invoke cell.set, then it can take arbitrary value, but any value, whatever value it takes, it will trigger UB here. Because, let me execute that here. So for any value x, so you provide the cell x, and then you retrieve the repository from the repository value, which is cell 0 because you just stored it. And then, but you see here, the P star own MR is already false because the cell x and cell 0. So cell cannot have two copies. So it's already false. So whatever x is taken, this triggers UB. So whatever value is taken is UB, so it's UB. So if foo function invokes this function, it automatically becomes UB. So that's why this refinement holds. Even though in the reasoning, I ignore this using the power of separation logic. Okay, so this is a mixture of unknown function call and separation logic and simulation. So this is always also termination. This program must terminate because the spec terminates, right? So if you want a divergent program, you have to put some operation, while star skip or while true skip or something like that. Then you can allow a divergent program. But here it's a terminating program. So in our tool, we support both induction and co-induction to verify those things. Okay. Let me check. Okay, finally, the interesting part is finally, we can eliminate this all assuming which we don't understand, and then get real spec. So this is automatic part. So here, if foo.foo does not invoke cell.set, then we know that every assuming guarantee matches. So our tool automatically check that matching, and then eliminate those things automatically. That's our cancellation theorem. So if foo.foo does, for first, the main function does not invoke this function, so there is nothing to match. And then foo.foo does not invoke this one. If foo.foo does not invoke this one, then nothing to match, so automatically match it. But if foo.foo invokes this function, then what happens is that cell.set has this assume and take part, but there's no corresponding part in this code, right? So there should be equivalent guarantee there. Then they met and that they can disappear. But since there is no such thing, if this foo.foo invokes this function, then our cancellation theorem cannot proceed. But if it doesn't invoke it, then we can proceed it and we can prove, we automatically get this one. So finally, we have a real spec to real spec. But in the middle, we use the imaginary spec to specify something interesting, okay? Okay, so let me see. So what time? So until 10, or I have half an hour? Okay, I think it's good. So I think this is a somehow important part so far, and the main ideas. So finally, we have by transitivity, we have this refinement, okay? And then I will show you two more examples of interesting specification using imaginary spec. So one is a logical atomicity. So in Iris or other separation logic, you can encode the logical atomicity in a certain way, but in imaginary spec, it can be very directly, easily specified. So for example, assuming certain atomic function, and there is some implementation, and this is spec, then usually what happens is that the function executes in multiple steps, and at some point in the middle, atomic action somehow, like a cast, if it's cast, the cast happens in the middle of the function code, right? So, and then, but the problem is that the resource that is needed at the point of atomic point should be given by the user at the beginning of the function, because in Iris, the pre and post condition is really pre and post condition. It's not middle condition. So you have to provide something interesting encoded resource that guarantees that you have ability to acquire the wanted resource in the middle, something like that. But here, you don't need to do that, because we can operationally express atomic section. So this scheduler.yield is some kind of, later I will show you, but it's adding concurrency to the model. So this is interference point where some other thread can be executed, right? So operationally, I know that this part is atomic section. So this spec as a single yield and single yield means actually in the implementation, you may have many different yield, but we can abstract into 3 sections: before the atomic section and after atomic section. And then precondition, usual precondition is given here, and post condition is given here. But the condition you need for the atomic update or whatever, that's given in the atomic section. So I can control the point where I require assuming guarantee. So the assuming guarantee does not need to be always pre and post condition. Anywhere you like, you can put the condition. Then you don't need any encoding. You just put what you want, okay? And then we already have examples verified in Cog, and with some concurrency example, it works perfectly, okay? So we don't need any fancy encoding. Another thing is interface abstraction. So you can also abstract even argument and return values. So thinking about some linked list example where the argument is a 64-bit pointer values, okay? And then you take a pointer value and update linked list kind of thing. So let's say add a front function, which it takes pointer and then value, and then it add this value into the list, okay? And then the spec, direct spec would look like this. Takes pointer and then value, and in your imagination, you choose corresponding mathematical list, and then you assume some kind of point to predicate, this point to predicate this one, and then you have a code which is purely working on the mathematical list only, without mentioning any P. Okay, so here LST prime, new prime will be mathematical append cons function, and then you choose corresponding physical address, which points to the new mathematical thing, and then you return. That can be your spec, and then you can verify your implementation in C against this one. That's possible. Actually, we have more complex examples, but and then the user of foo will have some code which is purely some code working on mathematical list only, and then at the invocation time, you have to convert the list into physical pointer, and then pass it to the function, and then get the physical point, and you convert it back to the mathematical list, and then you do every working on only mathematical list, okay? And then this kind of conversion we call virtual argument and physical argument. So here, this is all kind of generated code, not you don't need to write down. Using the interaction tree translation function, we can generate this code. So this is a virtual argument, and this is a physical argument because it's physically given. And this is a physical return value. This is a virtual return value. Okay, so and then our cancellation theorem automatically delete physical and the conversion everything, and you get only the code with the virtual argument only. So this function take a mathematical list and return it. This function pass mathematical list and get it. So we know that the behavior, linked programs behavior is same as linked programs behavior in C. Even though in C you pass the pointer values and then this spec you pass the mathematical list, their IO behavior are equal, okay? So that's just the result of our tool. This can be done automatically. So we have a generalized cancellation theorem, which it does also cancel out matching assuming guarantee, but also it cancels out the matching conversion between physical and virtual argument, virtual return values. So all canceled out, and you have only the virtual code only. Your top-level spec will be much more cleaner than implementation. Right? You can specify your program in as a mathematical function or whatever. Okay. So that's all. So that's a key idea. So at least I'm done key idea. So but there's another half of key ideas. But anyway, so maybe let me really briefly show you the demo. So it's our system. It's a really like it's in the Iris proof mode. So this say that main function, main module and cell IO module. This is the library module I linked together, and main implementation and cell A. So you see cell A. So this is a spec of a cell. This is also spec of cell. This is a spec of main. This is implementation of main. So as I showed you before, I linked the program together and then verify the refinement. So then what I have is here. This is the source program, which is the both imaginary spec. This is a target program of main, and then we have some Iris predicates and so on. And then if you execute, so here you see in the code we have assume. This is a code, right? So we can operationalize assume and guarantee. So everything is operational semantics, and then we can take steps. Steps L means steps in the source side. And then this is Iris command. And then I get, let's see. So I get L0 here, right, in Iris. So I will not follow everything because this is exactly matching with what I explained previously in the animation. So this is a stepwise experience. So inline. So inline is really jumping to the cell module. And then I execute. And then at some point, I will have a cell I. Okay, I lost the cell because in the middle I lost L, and then I invoke some same function at the same time, and so on. At some point I will have a cell I. Okay, so I will maybe stop at this point. Okay, now I have a cell I, right? So something like that. So I can complete following the same steps. I can complete the proofs. Yeah. Anyway, so let's go back. So it works really like Iris. So it builds upon our earlier tool, CCR, which is similar to this one, but doesn't support this arbitrary mixture of conditions and operational semantics. So Chris is somehow much more advanced than CCR. And also we employ a lot interaction trees. Without interaction tree, I couldn't imagine how to implement this one. And also without Iris, I cannot imagine how to implement this one. So we directly use Iris proof mode, just import it, or resource algebras, we just import it. We don't define, we just import it and use it, okay? But our theory is different from Iris, so we don't use the step indexing. It's a really simulation relation. So, but we can support a lot of features of Iris without step indexing. So we can support the ghost location exactly the same way. So user wouldn't feel difference. You don't see any difference. And they're also opening and closing invariant via fancy update exactly the same way. And logic atomy slightly different way, but also we believe we can support the same encoding, just we haven't tried. And then higher order predicates in a different ways. Instead of using step indexing, we can do my earlier work called the parameterized by simulation. So the key idea is that we can use parameterization to handle higher order or to solve cycles. So here we use similarly, we somehow parameterize over spec, then we can support higher order predicates. So we have a Landin's NAT example and other some higher order examples. And so far, I don't see any problematic example, but probably since this is not purely higher order like Iris, there might be certain challenging example, but I don't know yet. So all kind of example I can imagine is okay, but there might be a problem. But yeah. But the important thing is that if you have step indexing, the transitivity does not hold. So we cannot, we have to give up step indexing because we want to have a contextual refinement which is transitive, right? So in order to have transitivity, absence of step indexing is important, okay? Okay, and then, I think it's a good timing. So, and then the second part of talk, I will focus on how modular our system is, because as I have shown you, that each module has its own operational semantics. It's independent from other module semantics, right? So even we could link with this real spec and the imaginary spec. So this operational semantics and this operational semantics are very different, but we can link them together, right? And then we can pass arbitrary mathematical values around between them. So this is very powerful, and I will show you how to do that. So here, yes, we allow the C programs or OCaml programs or specification or model, whatever models, everything is expressible here as an interaction tree. And then we have a general tactic which works for every interaction tree. So even our general tactic works for C-Lite code, okay? And then it works under, also our verification is stable under arbitrary contextual module. So the verification result is very strong. It's composable with anything, right? So using this, what we can do is that we can encode a lot of meta-level features and concepts as a user-level module. So I will show you maybe 10 kind of examples, and it's really covering a lot of things, okay? So for example, we can add this memory module into the system, but without changing, the underlying system does not have any notion of memory. But we can add the memory system by adding memory module implementation. So this real spec is that it has an interface with a malloc-free, write, read, the comparison, and some other things if necessary. And it all specified as an abstract operational model written in interaction tree. So it's a mathematical memory model. And then here, the spec is some abstract spec with assume and guarantee, which will look almost identical to separation logic assume and guarantee. And I can prove this refinement as a user level proof mode. As I showed you before, just in the user level mode, the iris proof mode, you can just prove it. Then you have a memory now. If you invoke these functions, you can use this spec for your reasoning. We can also extend with the scheduler. We can add the concurrency, right? So the scheduler module will have a spawn, join, yield, get TID. So we already implemented it. And it's specified as an abstract operational model, which makes interleaving between threads. And also the scheduler algorithm, you can choose completely different ways. Either fair scheduling or unfair scheduling you can do. But for scheduler, we need some primitive support. So Chris provides primitive operations for basic interleaving. So it's a really primitive basic interleaving features. Then this scheduler can use it to implement your wanted scheduler, any kind of schedule algorithm you can implement. And then you can give assume and guarantee pre and post condition for each function as a spec. And then you can also prove it in user mode. Okay? You just add this user level module, then you have now concurrency. So you have a memory module plus scheduler module. If you link together, you have a normal concurrency. Okay? And also, even you can have network model. So we also implemented this interface, sockets, sender, receiver, listen, whatever, with just specified as some mathematical operational model. And currently, we only have UDP, but you can also define either TCP or both. It's okay. Just I think, if I remember correctly, we just have UDP model. And then you can give also pre and post conditions, and then you can also prove it in a user level proof mode. And you have now network plus scheduler, then you have a distributed system. Also, even you can have a scheduler for network scheduling, and each node can have a memory plus each node's concurrent scheduler. Then you can have a distributed system with a concurrent execution in each node. Okay. Now we also have a weak memory, because I also worked on weak memory quite a lot, so I know weak memory well. So we also implemented weak memory. So weak memory model here, and the weak memory spec here. We haven't verified this refinement yet. It's in progress. But it can be basically done in user level proof mode. So this model we based on our previous, my previous work, VRC11. And so this can be done, okay? And then weak memory plus scheduler, then you have a complete weak memory scheduler, and you can reason about weak memory programs. Okay, ComCert memory model. So we can also have a ComCert memory model here. Malloc free, write, read. It's really a ComCert memory model. So we just directly use the ComCert memory model definition exactly. We didn't change it, just the same definition. We just wrapped around it to make it to interaction tree style. So they just very shallow light translation from CLI memory definition to the interaction tree. So it's exactly the same memory model. And then we can add assume and guarantee for this memory model. And then actually we did more than that, because actually in this coming Friday, one of my students, Yonghyun Kim, will present at POPL', which is a ComCert cast, which support integer point casting. So it's a fully preserving all ComCert patches. We didn't miss anything. It's a full ComCert, but with the point integer casting. So here we have a model with the point integer casting, and we have a logic with the point integer casting. And so we also, I will tell you, so we verified the XOR linked list. Anyway, that's possible, and this is already done. So this can be done in user level proof model. And then now we have a C-Lite memory model. And then we also have a C-Lite code. So what we do is that given C file, we use a C-Lite parser to generate C-Lite code in core. And then we define the simple translation that from C-Lite code to interaction tree version of C-Lite. So also this is a shallow translation. We use original definition exactly same way. We didn't redefine. It's the same definition, just in the interaction tree style. And we call it C-Lite plus because interaction tree is better, so it's plus. But anyway, basically same. It has a go to, switch, break, continue, every feature. We didn't miss anything. It's exactly the same definition. And then you can imagine a spec with your own imaginary spec, and you can verify. So we verified, of course, user level proof mode. We verified XOR linked list, proper XOR linked list implementation. We fully verified, and also we linked the result, combined it with the ComCert result. So we have end-to-end verification from the top-level real spec down to real assembly code of C-Lite. Okay, that's our result. So this is done. So I will give a very quick demo on this if I have time. Okay. And also another point is actually the working on C-Lite is quite pleasant. So so our general tactic works very well, and I just added the 20 lines of extra tactic to just handle boilerplate code, and then it's really quite fast enough. I mean, it's not so slow, and then also reasoning is quite pleasant. So we could easily add the program logic for C-Lite, power of program logic to C-Lite easily. And we can do the same thing for other semantics as well. If you have your own semantics, you can just have a shallow translation from your semantics to interaction tree, then everything, you're done. You have a full power over discrete, or separation logic, iris power, and then or simulation power, and everything you can get for free. Okay. And then now more consistent. So also, since this is a termination preserving framework, so we can specify liveness and fairness. So in our previous work, we presented fair operational semantics, which is how to operationally capture notion of fairness. So we also defined the fairness module, which has a single interface function called fair, and which has some operational semantics following this work. And we have also fair module specification, which is LILO. It's a conditional accepted at UPSLA 25. Oh, sorry, 25. Yeah, it's inconsistent. Yeah. So we can import that specification into here, and we can prove also refinement as a user level proof mode. Then we have a way of specifying fairness, and then way of reasoning about fairness and everything we get. Okay. So we can now specify liveness, fairness, and safety in one go. Our specification talks about everything. Okay, and then we can verify our verification, actually verify, respect all the features, okay? So, also we can define fair scheduler using fair. So we can change the scheduler module, we can define another scheduler module, which using fair module, you can specify fair scheduler, like no thread is starving, something like that. So you can do that. And then also we can do prophecy. So this is like a halfway goal. So we are very sure that this will work, but even though we haven't completed the proof yet. And the idea is that we can have a prophecy module with the 3 interface, new, resolve, and close. And then the implementation is just simply every function spot is just skip. So invoking new, resolve, close anywhere in your code is completely identical code because it's just skip. But in the refinement, in the spec, you have new resolves close with a certain assuming guarantee, which gives you full power of prophecy reasoning. Okay? And then, but unfortunately, this refinement only holds on the real spec. If it includes a take, like imaginary non-determinism, this refinement does not hold. There is a counterexample. And intuitively, somehow we know that that's a wrong reasoning. So what happens is that in our scenario, we always start with the real spec, and then go into the imaginary spec, and then finally jump out of imaginary spec and then go into the real spec, right? So in the first place of lifting from real spec to imaginary spec, you can insert prophecy variable anywhere you want. Because at that point, your context will be all real spec. So you can insert, at the first time of lifting, you can insert the prophecy variable anywhere. It's completely free. There's no ghost code at all. Just you can add it anywhere you like. Then later on, not immediately, later on reasoning in the upward, you can anytime when you want to reason using prophecy variable, you can just use this assuming guarantee. Then it gives you full power of reasoning about prophecy variable. And also this interface is slightly more general than the Iris's previous work. I mean, we really like it, and then just so we generalize the interface so that we can have more power. But that's not essentially very different, but somehow this refinement without ghost code is something new. And we are halfway through this proof, but the proof is not user-level proof mode. As you see here, it's not normal contextual refinement. It only holds under real spec, and then this proof is very, very complex co-inductive proofs. A lot of co-inductive techniques that we developed, we fully utilize it. Anyway, it's a not easy proof, but we are sure that we can finish it. I mean, we have very clear idea how to prove it, and so hopefully we can finish it soon. So that's almost all. Okay, so I have to stop here. Let's see. So status of Chris. So we fully developed Chris framework. There's no limit at all. It's fully done. And then some of the extension modules I mentioned are completely done, and some are in progress. And also our work hasn't been submitted yet. We are preparing submission. So tool is already usable with many examples. We have many, many examples, but no documentation. So we are not going to release it now. But if you are interested in, I can give a private access so then you can play with it. Okay, so just tell me if you're interested. Finally, a lot of people I have to thank. So for Chris, so many people, because many students are interns, it includes every intern. But anyway, so it's basically all of my current students. And the CCR is our predecessor, where Yongju and Mingi was the main guy who developed CCR in my group. And then also Michael and Derek helped us. And then Archimage and Consult, which will be presented at POPL on Friday, also these students. And then really thanks to Iris, interaction tree. That's a really cool tool. Without it, even though we had the idea, we could not implement. We could have not implemented. But anyway, thanks to this one. And Paco is my own tool for co-induction, but we used a lot. And I just missed one more tool. I thought about it in the middle, but anyway, probably there is more tool we used. Okay, thank you. Yeah.
Are there any questions?
Yeah.
So thanks for the nice talk. It looks like a very cool tool.
Yeah.
So what are the limitations of Chris?
Limitation. Let me see. Somehow it can be a bit slow, and then if we can make it faster, that would be cool. But it's a quite early version, so there is room for improvement. And then also, as I mentioned, the higher order thing. Currently, we don't have step indexing, so if there is a possibility that certainly somehow complex way higher order predicates, we may have trouble to express it, but I don't know any example yet. But maybe there, and then my belief is that there should be a solution. So if we see a challenge, then it may not work directly, but should be able to find the solution. But that's my belief. But currently, it's not fully like a truly higher order thing. Okay, yeah.
Hi, thanks for the talk. That sounds cool. So if you want an interesting example for higher order ghost state, check out the Rust Belt lifetime logic.
Lifetime logic. Okay.
We're having some fun with higher order
but
ghost state
there. But I think that's use case. Oh, use case I should have mentioned. So we use the use case Neil anyway tool.
Modular.
Yeah, Modular. Yeah. We use the same idea basically here. So didn't he use the Modular to handle that one?
Okay.
But then we can do it. We follow the same.
I don't know if I don't know the state of.
Okay. Thank you. Anyway, so yeah, we can check it.
Anyway, but I had a question. So you had this refinement earlier in your first example. There was this foo function, and you said something about foo can't use cell or something.
Foo shouldn't.
Like, how is this expressed formally? Right? I guess this is a side condition you have omitted on screen.
Yeah, good.
Is this like a syntactic check?
No.
Like what does it mean?
Interaction tree, we can do that. So what we did was that in this final refinement, what we did was that given foo.foo function, we just added a wrapper function which makes a call to cell.set to skip. So that in the interaction, it's given as an interaction tree. So you can have a event handler. So you just handle the call to the cell.set. You just intercept, and then just turn it to skip. So we just proved that conversion after that conversion. So that by construction, this cannot call thing. But if this function didn't call it, the handler does nothing because the handling only intercepts that call, right?
Okay, so the chain is like I have this foo module, and then I have foo module wrapped in this like cell hider.
Right.
This refinement, which is where I prove that I'm not using cell.
Oh, the refinement between you mean the two? This one, or?
Yeah, I guess I have to prove that my cell hidden foo refines the original foo to show that I can go in the chain, right?
Oh, yeah. You may. But if by construction, if it doesn't occur, I mean, it will be just a
should be a simple proof. But and then I have the cell. Okay, this does remind me a bit of dim sum, which also has these fun wrappers that you compose while refining and composing. I don't know. Just putting that out there in case someone finds it interesting.
Yeah.
But thanks anyway.
Yeah. Okay.
So I wanted to ask about this cancellation theorem.
Yeah.
Like, what exactly do you mean by matching? Like in this example, you have an A but no G. So what's matching?
That's correct. So A is really the initial condition. So that's actually proven by the user directly, and all the other things should match. And A is the only exception, actually. Yeah. So the main function's first condition is the only exception. So that
and how are you getting rid of the cell module?
It's also interaction tree thing, because actually this code is all generated by this. The code that is intended to be deleted is not written by user. So user has a certain event, then the event handler can generate that boilerplate code, and then later the cancellation theorem just delete that event using another event handler. Not event handler, just you drop the event handler, then you get original code. So somehow this boilerplate code, like this assume and guarantee and take things are mostly generated by the interaction tree event handler, and then also deleted automatically. So that's how we handle the elimination. So without event interaction tree, I don't know how to do that, because syntactic search kind of thing is ugly, right? But yeah.
I just wondered about the automation. So is your tool, if I'm a newbie to this, is it able to somehow automatically hint at which are suitable suitable imaginary specifications? So how to come up with this new annotations? And so once you have these annotations, these steps that are done in this rock proof here, so is this generated automatically for you, or do I have to do this all manually?
Which one all manually? You mean the, sorry, I missed the, text, this one. This one currently manually. Yeah, currently manually. And then, but this is really, our simulation is iProp. iris prop predicate. So this is really just iProp. This whole goal is iProp, but just displayed in a more readable way. So everything is iris prop. So any iris predicate automation tool will apply here. It's just simply iris prop, and everything is iris. So that will work. And also another, maybe my vision is that this kind of proof is done by, this is done by me, but after reading someone can do this by reading tutorial and then this simple things. I think LLM can do that too, soon, like really in a near future, because it has a logical reasoning power now. So we can just teach it LLM how to use our tool, and then it can probably prove many things. That's my kind of vision.
Okay.
Hi. At one point, you gave the impression that, or you pointed out that it wouldn't matter what semantics you have. You could, this would be completely general.
Yeah.
But the examples you gave, it seemed mainly for like imperative languages. And would it work for any kind of semantics? You could do the same thing, or does it have to be, this pre and post condition logic and things like this?
Oh, okay. So I don't think this tool has any kind of it's a stick to imperative program, because we use the imperative program as examples, but it's just an interaction tree. It can also we have so you can define high order functions in Coq and then verify against it. That's also possible. And also we can encode some kind of OCaml syntax in interaction tree. And then anyway, it's operational semantics. We have an induction, co-induction, and all kind of general reasoning tool we support directly. So I don't think I think it's similarly also there is a separation logic for functional languages, right? So similar approach we can do. So I don't think there is a fundamental limitation. Yeah.
So this is, as usual, very interesting work. So about the modularity aspect that you talked about in the second part, I'm trying to get a sense of what that will allow you, what practically you can do when you mix, for example, say, weak memory model module with other modules, because my experience in Iris, at least, is that, I mean, yes, of course, you can build versions of Iris that work with weak memory. We've done that many times, but then it can radically change the kind of reasoning principles that are allowed, right? For example, regular invariants are no longer.
Sorry. For example, what?
For example, invariants, right? Standard invariants no longer.
Sound invariant. Invariant.
Invariant mechanism, no longer is like sound, right?
No. We
need to change. You need to adapt.
So
I'm curious how you end up.
Oh no. Okay,
like in Iris, you build up layers of new abstractions for given. But I don't see how these would interact.
Okay. So if I understood your question correctly, I think the way we handle invariant, those things are very different from Iris. So Iris has some kind of fixed physical state predicate or something special. But in our case, we don't have such a thing at all. So our resource predicate is not related to physical state or nothing at all. It just goes. It's not related to anything. But you can relate certain predicate into physical state. Physical state here is only module state. So you can, for example, memory module case. So the memory module predicate, for user's viewpoint, it's completely nothing. It has nothing to do with the physical state or anything. It has just a rule of resource algebra. So you cannot have L together, that kind of rule only. It's not related to anything. And only this memory module can relate it to its physical module state. So actual physical module state will be a module local state of this module. So every points to or memory will be defined as a mathematical map, whatever in here. And then you can only relate the predicate into your module local state only internally, and user does not know existence of this one. User only verify against this this spec. So it means the user's case, you haven't seen this thing at all. Just existence doesn't matter. You verify against this one, and then this verification guy verifies that actually this spec contextually defines this one. So this the connection happens only locally, and then it's by something called IST, state invariant. So it's a modular local state invariant we have, which is conceptually correspond to state instantiation thing in Iris. But each module can have its own custom relation so that it's not visible to outside. Does that make sense? Or
let's take it offline.
So anyway, the result is that we have an example. It works well, so we can combine anything together. Anyways, yeah, it works so well.
So this pattern of connecting, like rather than using a pre and post condition, using operational semantics or something that looks sort of like operational semantics, seems very similar to using weakest precondition inside propositions. Do you know like how this, like you could also write a lot of these specs in that style?
Okay, good point. Yeah, that's a good point. And then actually, that's a good question. And then the answer is that the weakest precondition, the condition in the middle is only visible to verifier, not client. Client only see pre and post condition. That's the problem. In our case, client see the middle condition. Client can use. So look at, for example, this spec. This information is visible to the user. This is a reasoning principle to the user. But in the weakest, even if with the weakest precondition, user only see pre and post condition. That's all.
But the pre and post condition could be it could be a weakest precondition of y equals input of cell y. You know, like you could interleave.
But that's implementation code. That's implementation code. So you are verifying against the implementation code.
No, I mean in the spec itself, you could have weakest preconditions there, and that would be a way of expressing these kinds of specs.
I see. Now I get your. So your point is that somehow encoding this whole operational flavor thing as a pre and post condition. Okay. Yeah. That can be that can be another approach, but I don't think it has this full power of vertical composition. So we can abstract program. So actually, the power of this one is really we have a code semi-abstracted. Some code is abstracted as assertions. Some code are remaining same, right? Like here, the input is unknown function call. So input is not input doesn't have any pre and post condition. Input is just a function call, right? It's a code itself. And so I have a nice example where sometimes network. So actually, this is an ongoing project. You have the distributed system, and then you have Raft algorithm, and then each node may have completely different Raft implementations. And then the way we verify is that we give a reference implementation, and then we verify the whole algorithm correctness based on reference implementation. And each node, just to prove its implementation, refines the reference implementation. And this refinement even requires a certain pre and post condition about network things and so on. It's not purely like a compiler correctness. So this kind of decomposition is possible, and we can have a multiple decomposition over in various different directions. Okay, thank you. Thanks.
Thank you again. So
okay, thank you.
The microphone, is it on? Okay.
Okay, so the next speaker is Aina Lin-George, who will tell us about the next-gen modality.
Thank you so much. So thank you, everyone. Yeah, I'm Aina, so I'm going to present our work today on the next-gen modality, a modality for non-frame preserving updates in separation logic. This has been joint work with Simon Fries-Vindum and Lars Birkedal. So in general, I think we can all agree that the frame rule and frame preserving updates are very central to separation logic. So if we consider the very classic core triple for a store operation, we can do this update because we have exclusive ownership, so that's what the points to predicate means, over some location L. And what this means is that it's always safe to apply the frame rule that we all love. And in general, the frame rule and frame preserving updates are very suitable to express any kind of local change to the physical state. Right, so here we're only updating L, which is why it's frame preserving. However, in general, not all changes are actually local. Right, so sometimes we will have certain setups that lead to global sweeping changes of the physical state. So some examples include machine crashes, in particular in the presence of durable memory. This might deallocate a bunch of memory. It can also include garbage collection, which also deallocates a bunch of points to predicates. And finally, another example include the frame deallocation if you have a language with a call stack. And none of these updates are necessarily frame preserving, right? Because they're making these sweeping global changes to the machine state. So to see why this is an issue, I want to look into more detail of this third example. So let's imagine we have a language with a call stack. Here we have an expression, return 2. And what this means is that we're going to return 2 frames down, 2 frame k. So essentially, this instruction is going to deallocate frame I and j. All right, so let's try to describe a triple for this. Maybe a first, well, quite naive attempt is to say, well, since this instruction executes in the topmost frame, naturally, they might own the points to predicate or the resource of the topmost frame. Okay, so we can imagine that the rule looks like this, where essentially the frame gets deallocated and consumed by return. But of course, this is not sound. Right, so we can apply the frame rule with j, but since j also gets deallocated, this doesn't work. And the only way around this, in this case, is that we must describe a rule that contains all of the deallocated stack frames in the precondition. Now, the precondition must have all of the resources that we're actually deallocating. And while this rule is sound, it's maybe not entirely satisfactory. It means you always need to carry these frames around for all calls in case they return to a lower frame. So it's not like as modular as we might want it to. And this gets even worse in some of the other examples. So for example, if you have crashes, then you essentially need to put all of the resources that might get cut by a crash somewhere in your logic. I mean, you can't just carry them around all the time. It gets really difficult. Okay. So in this work, we're going to present an alternative solution with non-frame preserving updates. So more concretely, the main contribution of this work is the basic next-gen modality. It's written here with the squig, and I will explain later what the T means. But essentially, this modality will define some kind of, or will express some kind of global event. So if we look at our return program from before, our goal is to be able to describe a triple that now simply marks the continuing program C with this global event. So note here, we don't need to carry around the resources that we are deallocating. Instead, we're going to put this global event, which here is a pop, before the rest of the program. Now we are defining the next-gen modality in Iris. So I'll give very brief background into Iris. I will especially mention this third part because this is important for the definition. So what is Iris? It's a higher order concurrent separation logic framework. It comes equipped with a bunch of modalities, so namely later modality, which means a predicate holds after one step, so that's the triangle. The always modality means something holds at every step or always, and the frame preserving update modality, among others. Next, it also comes with Iris invariance, so that's written with this box. That means that the assertion I holds at every step of execution. And finally, a big draw of Iris is that it comes with user-defined resource algebras or user-defined ghost state. And what this means is that users of Iris can define any kind of resource they want by defining a resource algebra, so here written as MI, and add it to the collection of resource algebras that you work with. So in general, we're going to write the ownership of some resource A which is part of some resource algebra Mi with the dashed box. Right. So let me get into the technical details of the basic next-gen modality. How is it defined? So let T be some transformation of a resource algebra Mi. Then the easiest way to see how we define the basic next-gen modality is to look at the introduction rule, which looks like this. Right, if we have a resource A, where A here happens to be the resource algebra Mi, then when we introduce the next-gen modality with transformation T, we just apply T to A. Now note, this modality is not frame-preserving. Right? So in particular, this statement does not hold. And that's because T might actually have an effect on the resources below it. Right? So if Q has some resource A in it, then we cannot just freely put it under the modality, because T might transform it. Okay. Now, the definition is quite simple. This is it. So let's look at some of its properties. All right, so first of all, we've already seen the introduction rule. Also, this modality is monotone, so that's the second statement. And thirdly, we can compose these transformations together. Next, it also behaves quite well with the existing iris modalities. Okay, so it commutes with later, and it also commutes with always under some condition that I'll not get into the details of, but it is very sensible. Okay. And at this point, I want to take a small sidebar and give a small comparison to what is perhaps one of the most related works currently, namely perennial. So what is perennial? It is a framework for verifying concurrent crash-safe systems. Okay, so this falls under one of these examples I mentioned earlier with crashes. And indeed, they also define a post-crash modality, it's written with this diamond, to express the way in which resources change due to a system crash. This work is also done in the iris framework. Now, unfortunately, the post-crash modality has a couple of limitations. So firstly, it doesn't commute with the box modality. And also, it doesn't have interaction, very well-defined interaction with custom ghost state. And I mention these limitations because the basic next-gen modality solves these, essentially. Okay, it has very well-defined interaction with custom ghost state. And it also commutes with the box modality. So that's it for the most basic version of the next-gen modality. But I mentioned how one of the draws of iris is that users can keep defining new resource algebras. And in fact, it means that in practice, you don't just have one resource algebra, you have a collection of them. So what does that mean for our next-gen modality? Let's say, well, we have a collection of resource algebras. In iris, it's usually defined like this. You have a product of n different resource algebras. And for each of these, you will have multiple instantiations of the same resource algebra. Okay, so this map is to define multiple instantiations of Mi, each parameterized by a ghost named gamma. And we're going to essentially do the same for the next-gen modality. Okay, so we're going to maintain this product, again with a map parameterized by gname. These will essentially align. And for each of them, we might define a transformation. So in fact, our introduction rules look like this. If we happen to have a gamma that is within this map of transformations, then we look it up and apply it. If gamma happens not to be in the map, then the introduction rule does nothing. Okay. Now this has been quite abstract. So let's go back to our case study from the beginning, the call stack deallocation, and see how to actually define a usable next-gen modality. So to recall our goal, we want a rule that looks somewhat like this, with this global event that marks a pop event. And really, the game here is to define the right transformation T that will define this event. We introduce the language that we're working with for this case study. It's called stacklang. The operational semantics is a fairly standard lambda calculus with continuations. Except it also has a high-level representation of a call stack, S. S here is a list of frames. Each frame is a small map, and the topmost frame is to the left. Now, frames are pushed upon function calls. So if we have a function call here, we're going to push an empty frame to the head, and they're popped upon function returns. So in the simple case, if we just return one step down, we're going to remove f here, which is the topmost frame. However, I mentioned that we have these continuations that let us skip frames. So more generally, what does a return look like? It is an invocation of a continuation, written like this, that targets the ith frame from the top and continues the continuing program k. Now, k here is an evaluation context that takes v to continue. So v is the return value. And this instruction now pops the I topmost frames. Okay, so we're cutting multiple frames at once. Now, the first step for defining our program logic is going to be defining the ghost state we work with. There's three main ones, so three different resource algebras. One for heap locations. This is standard points to predicate. Next, we have one for stack locations. They're additionally going to have this k, which indicates which frame they belong to. And finally, we're going to have a resource algebra to write to express the size of the stack. So the symbol here at the bottom left means the stack has m frames. Okay, let's look at an example rule. So first, we start off a bit simple. Stack allocation. So stack allocation needs to have at least one frame in the stack. So we assume that we have the resource that expresses the size of the stack being m. M must be non-zero. And in the post condition, we get a fresh points to predicate of a new stack location in frame m-1. Now, more interestingly, is the rule for return, or the invocation of a continuation. Okay, so since we are returning to I frames from the top, we need to know that there are at least that many frames to pop from our stack. So we assume that the size of the stack is m plus 1. And in the continuing program, we have a stack size of m in our continuation. And importantly, we need to mark this event to say that we are deallocating stack frames. All right. OK, so we've now gone to the fun bit, is to define the actual transformation. So we want the transformation to simply remove frames from our stack S. And we're going to define it as scut. Of course, we're defining many next-gen modalities here because we want one for each possible number of frames we're cutting. So scut n takes the n as a threshold now, and will remove every stack frame above it. Okay. We can now define the modality that we're going to use in the program logic. It's written with this n as a parameter. And essentially, we're going to look up I, which is the index of the stack resource algebra, and we're going to insert scut n at that location. Okay. Let's look at some properties. Right, so first, since this is really only about the stack resource algebra, we can just introduce it in front of the heap resource algebra without any effect. Next, if the stack location is below the threshold, right, so if we are cutting all frames from n and above, if the k, which is the frame of our points to predicate, is below, then nothing happens. However, if it's above, it gets consumed. Okay, so in this case, the introduction rule essentially consumes the points to predicate. This means it gets deallocated. So what is the rule going to look like? Finally, we simply say that since we mark the event as cutting all frames above m, then we have next-gen m in front of the rest of our program. All right, so this is our rule. Let's use it in an example. Now, I hope it's large enough to read. I wanted to go through the whole example really to highlight this point that we don't need points to predicates for the frames that we're deallocating, and why that's nice. Because we have a program here. Okay, use my mouse. It is a function application of a function that returns to frame n from the top. And locally, what it does, it's going to allocate a new stack location. Then it's going to do some computation over it and importantly, it's going to read from this global G before it returns. Right. Now, the only assumption we want to know is what happens to the continuing program K. And here, K only needs to know that the stack size is M, if it starts out at M plus N, and that G still exists. Okay, so our assumption is that given the stack size M and G points to 1, we can continue the program K. All right, so we do a function call. That means we are pushing a new frame onto the stack, so the stack size grows by 1. Note here that our continuation shifts because we are now targeting the n plus 1th frame from the top. Next, we allocate this new local stack location at frame m plus n. We then do a substitution. Okay, so that's fairly standard. And next, we do the actual computation. So I've skipped some steps here, but essentially we load from L and from G, and then add up the results together, which gives 43. And we've now reached the important and fun part of the program, which is the return. So we apply the return rule, which gives us this triple. Now here, I'm cheating a little because I'm using Hoare triples instead of weakest preconditions. But this is essentially meaning that we want to, in order to introduce this next-gen modality, we're going to need to introduce it in front of all the relevant resources in the precondition. Right, so in practice, in the iris proof mode, you end up with this obligation. Right. And here in the first case, well, this modality doesn't affect the stack size, so this is introduced very easily. Same for the heap. But for the stack resource algebra, right, since this threshold is above M, this whole location gets deallocated. Okay, but luckily, we didn't need this resource for our assumption, so we just continue. Okay, and we can use our assumption. However, what's really nice here is that our spec for this function doesn't need to mention anything about the frames of m plus 1 all the way to m plus n. Okay, so it's very local. Okay. So let me give 2 final remarks. Right, the first one, I really emphasized how nice this was, but what do we lose? And it's quite severe, because we do lose the frame rule, at least in this way, that we integrate the next-gen modality with the program logic. And to see that, we can see this with this counter example. So let's say we return and pop the whole stack with our return statement. Then, of course, we can't apply a frame rule using any stack location. That would be unsound. Right, so we do need to lose the frame rule, but this seems overall much too restrictive, especially because we have all these resources that are independent from stack locations. Okay, so we do set up a way to recover the frame rule. In particular, resources that are independent of the possible next-gen modalities should be able to be framed away. And in order to express this, we introduce an independence modality. It's defined on top of the basic next-gen. It expresses that some assertion P is unaffected by next-gen modality N. And our frame rule can then look as follows. Right? So if we have a frame R which is completely independent of any possible next-gen event that would happen, then we can apply the frame rule on it. The second remark I wanted to say is another big plus of the next-gen modality is how well it behaves with the existing iris infrastructure. Right, so I already mentioned that it behaved well with existing modalities. There are also some very interesting non-trivial interaction with invariants. So iris invariants are implemented using resource algebras. So it is completely possible to define a transformation for that resource algebra for the invariants. And that means that we can now define a new type of invariant that allows us to contain resources that might actually be deallocated or affected by transformations. So in the paper, we introduce such a variant of iris invariants, which support non-trivial interaction with the next-gen modality. Just to give a bit of flavor, we have an invariant that is annotated with a threshold n, and this essentially describes the lifetime of the invariant. So if k is below that threshold, then we can put the k points to predicate within this invariant. Now this is just for the stack line, but we also define this in a sort of language independent way, same for the invariants. And you can play around with it yourselves. All right, so in conclusion, we have extended the iris-based logic with a new modality for non-frame preserving updates. we've integrated the new modality in a program logic for a language with non-local updates as a case study, where we show how to recover a version of the frame rule. And also we show how we can support non-trivial interaction with iris invariants. Now all of this is mechanized in Iris Rock, and it should be available online.
Thanks for the talk. So in your last slide about the frame rule, how do you reason, how do you prove that your a concrete predicate is independent? Is it easy?
Okay, that's a good question. So we have set up a bit of help for that. Like there's some, similar to the iris proof that can allow you to do this. But essentially, yeah, you need to show that you can introduce the next-gen modality in front of it. So the proof obligation is that what happens when I introduce it, is it the same afterwards? With the support of the iris proof mode, it does become rather seamless. So if you've set it up properly, then you just get your instances of the type class, and this happens freely. And in fact, it's also integrated with the frame rule. So you can do an iframe, and it figures it out itself.
All right. So this is a joint work with Jose Bachelor Almeida, Tiago Oliveira, and Dominic Unruh on leakage-free probabilistic programs in Jasmine. So let's start with the motivation. Let's imagine the following toy system. So we have a server, and this server keeps a secret, which it is willingly can give away if you guess a password. And the password is sampled uniformly at random, and is 256-bit string. And let's assume that the only possible attack vector for the adversary is to guess the string. So for such a simple toy system, we can actually prove that it has kind of a galactic security. So the probability that adversary guesses and gets the access to the secret are negligible. At the same time, it's worth saying that for real systems, security might crucially depend on the implementation details of the server, even such a simple one. For example, the optimizing compiler might decide to generate machine code which checks equality between the secret and the guess until the first difference is encountered. And in this case, if adversary can time responses of our server, then it can figure out the secret in a byte-by-byte fashion and steal the secret during the lunch break. So what we're having is we have a discrepancy between the predictions of mathematical model and the real-life implementation. And this illustrated attack belongs to a family of side channel attacks, which include such attacks as timing, cache, and power analysis attack. And so the challenge which we tackle here is the question on how to prove that an executable of an actual protocol is correct, cryptographically secure, and is free of side channel attacks. And we would like to do this all at the same time within the same environment. So one way of doing this is to use Jasmine programming workbench, where Jasmine is a programming language which combines high-level and low-level constructs to support so-called assembly-in-the-head programming paradigm. So programmers in such paradigm have access to low-level features like instructions, scheduling, registers, stack, but at the same time it has natural access to the high-level abstractions like functions, arrays, loops, and so on. Let's look at the overview. How do you work in Jasmine? So the important thing is that Jasmine code can be extracted via compiler to the EasyCrypt theorem prover with leakage annotations, where leakage annotations accumulate all the informations which attacker can get to through side channels. And in this work, we focus on timing attacks, but everything which we say is not specific to timing attacks. It can be generalized to any side channels. And originally, in Jasmine, the leakage analysis was only performed on deterministic programs, and recently it was extended with some sampling primitives. And so we would like to see how to prove formally absence of side channels for probabilistic programs. So let's look at the example. So here on the right, you see a program which tries to sample a bit uniformly at random. So you see some details, but the really important part is that we're using the built-in primitive random bytes to get a random byte. And then we're just checking if the sample byte is smaller than 128, in which case the result is 0, and in other case, the result is 1. So here, the important thing is that we have no inputs, and we would like the output to be secret. Now, by using the compiler, we can extract this code to EasyCrypt theorem prover, in which case it generates a module with a procedure where all the constructs from the Jasmine were translated, but at the same time, the code is annotated with leakages. So now you see that at every step we're accumulating some leakages, and this is over approximation of what kind of information adversary can get if they would time the program. So the highlighted leakage annotation in red is actually the problematic one. So it happens because of the conditional which we use, and as you see, it leaks the Boolean which goes into the conditional. So in principle, if adversary has access to that information, then they know fully what is the output, what is the secret output of the program. So we can try to do better and change the program slightly, in which case, instead of doing a conditional, in the same fashion, we sample a byte, and then later we just do the bitwise AND of the result with the number 1 and return it. So in this case, if we instruct compiler to produce the leakage code with the leakage annotations, then you can see that intuitively the result of the execution and the leakages which are produced are independent. So the challenge is how to formally prove that probabilistic program is free of leakages. Before answering that question, we can look at the prior definitions from the literature, where we can, and more specifically, so-called cryptographic constant time programs. So for this definition, we assume that F is a deterministic total program in Jasmine, and then when it's extracted, then we compare these two probabilities. So the program F, it depends on it has public inputs and secret inputs SYN. Checking equality of probabilities which are produced for particular leakage, we're asking whether the leakage is produced in one case. Hello? Oh, now it works. Okay. Oh yeah, I think now it works.
Okay, cool.
Yeah. So for most of the programs for which this property holds, the cool thing is that it can be derived fully automatically by using the simulation tactic. But the question remains whether it's an adequate definition for the probabilistic programs. Here, the important thing to notice is that what intuitively this definition does is it checks whether the leakages depend on the secret inputs. So in the first probability expression, the second probability expression, the secret inputs are different. So if this probability are the same, then intuition is that leakages are independent of the secret inputs, in which case we can say that it's cryptographic constant time. Okay. But let's look at our naive bit sampling. And then we immediately see that since there is no inputs to this function, then the previous definition is trivially satisfied. So the output, in a way, the output which we produce in this procedure is being generated. It does not depend on any secret inputs, but kind of is generated within the computation inside the procedure. So this definition is no good for probabilistic programs, and we must generalize. To do that, we propose a kind of semantical characterization of leakage-free programs where we define two probabilities. The probability W is a probability of producing a particular output A, where the probability V is a probability that we generate the output A and the leakages L. And then we say that the program F, which is a total program, but now might be probabilistic, that for some there exists a function G and compute probability V divided by W. So given that we produce an output A, the program produces also the leakages L, and that this conditional probability depends only on the public inputs and the leakages. So we are not allowed to access the secret inputs during the computation of this conditional probability. The important thing here is that for most of the cases, this definition is really annoying to prove because it's existential in this computation of the conditional probability. So for most of the cases, it would be hard to apply. But the good thing about this definition is that it's inspired by probabilistic non-interference, so it has really clear it has really clear semantics. For example, for our program random bit, which is very simple, we would be forced to define the function g, which inside has to define a constant which is actually fully describes the leakages which are being produced during the computation. So in some sense, any change to this procedure would break the proof of leakage freeness, and you'll have to go and, again, characterize the accumulated leakages differently, which is very suboptimal for big actual cryptographic primitives with which we are working. So the next challenge is, can we define a probabilistic leakage freeness in the equivalent but somewhat auto-provable way? And for this, we give this definition number 3, which is phrased in terms of probabilistic relational Hoare logic, which relates to programs. So the program on the left is just a single run of the function f, which produces the result r and the leakages as it's supposed to. The program on the right is a little bit different. So first, it runs the program f in the environment where it generates only leakages, but we ignore the result. And then at the same time, we run this program again, but without generating a leakages, but only generating the result. And the statement says that if for such programs we start in the same state, and then they produce the same leakages and the same result, then we can claim that this program f is leakage free. The good thing about the number 3 is that, again, we restored the of the programs. It's going to be easy to prove by just simulation tactics provided by EasyCrypt. So we are in a good shape. And then this is the example of such proof. This proof is not going to change if the program on the right will be too much different. So the only thing which happens here in the proof script is that it sort of runs the simulation of the program in the PRHL. The important properties, which is the main contribution of the paper, is that we show that definition 2, semantical characterization, and the PRHL characterization, definition number 3, are equivalent. Moreover, the second property says that it's actually a generalization of the constant time. And moreover, for deterministic programs, both definitions, the constant time and then probabilistic characterization, they coincide. And the hardest proof in this formalization was actually the proof of the compositionality. So we proved that if you compose two programs which are individually leakage-free, then they produce a leakage-free program. And then, but we tried to push the limits and actually apply these definitions for somewhat more complicated use cases. And for that, we decided to study rejection sampling. And then, for those who are unfamiliar, so rejection sampling is the approach to create probabilistic distributions out of some given prior distributions. In our case, in our case study, what we took is that we have a primitive which generates distributions whose cardinality are powers of 2, and then the goal was to generate distributions of uniform distributions of arbitrary size. And the goal is to prove that this is actually leakage-free. The challenging aspect for this program is that the algorithm doesn't have a priori termination bound, which means that it only terminates with probability 1, but we don't know the upper bound on how many iterations it is gonna run. And then actually for such programs, it turns out that for both definitions, it's challenging to prove leakage freeness. So for definition 2, we actually need to fully characterize the structure of leakages. So it has to be an explicitly defined function which depends on the number I, where I is the number of iterations. And for the third definition, a PRHL characterization, we need to use some clever tricks based on Bernoulli distribution, where we need to detach generation of the leakages from the generation of the actual output. Moreover, another challenge which remains for these definitions actually proofs of leakage freeness for non-terminating programs. So everything which I said so far was only about programs which terminate at least with probability 1, but for non-terminating ones, the problem is still open, at least in the setting of Jasmine. And this brings me to the conclusions. So what we did is we defined two novel and equivalent definitions of leakage freeness for probabilistic Jasmine programs. We showed that they generalize the previous cryptographic constant time notion. We also proved that these are compositional. And we showed on some use cases that PRHL definitions for most of the programs which do have a priori termination works really well with the simulation tactics and can be proved automatically. And then, but still, for programs with no a priori termination at time, both characterizations are tricky, and the question on non-terminating programs is still open. And that's it.
Are there any questions?
Thanks for the talk. Can I go back to definition 3?
Yeah. Yeah, sorry.
Yes, yes. So in PRHL, the way you prove these equivalences is by tactics that allow you to align the samplings on both sides and then use a coupling rule, right? But there you have two programs on the right-hand side, one program on the left. So you're going to have twice as many samplings on the right.
So how does this? I don't really hear you.
So when you prove equivalences in a PRHL, you align the samplings on both sides.
Yes.
But usually. But there you have twice as many samplings on the right. Can you say a bit more about how this proofs work?
Oh yeah. So I mean here the important thing maybe which I only briefly mentioned is that so here the first invocation of the program, it only generates the leakages, and we fully ignore, so it's a distribution of the leakages. But the result is ignored of what it's produced. While on the second run, we ignore the leakages, so leakages are not produced, but the result is produced. So in a way, you have a fully two detached computations where one first run of it generates leakages, and second one generates the result, and then independent. The important thing here to see is that when we produce the leakages, then the secret inputs are different. So we're producing leakages out of the secret inputs which are different from the program on the left. So that's kind of ensures the difference between. So I mean, it ensures that leakages do not really depend on the secret inputs in this case.
Okay, maybe I'll ask later because I asked it and yeah, thanks.
Maybe this is just a clarification of that previous question, but what is XTRI in this?
XTRI is the same program, so it's the equivalent program to F, but the one which does not generate leakages.
So you just automatically generate two versions of every program?
Yeah, it's a compiler-produced program which is equivalent to the adjustment program, but just without leakage annotations. Yeah.
Can you go back to the definition 2,
yes,
please? Right. Here you quantify about the secret input, the private input, but also about this M. What is the M referring to?
Sorry.
The M in bold.
Oh, M in bold. So this is the initial state of the module, which, I mean, in this case, it's not too relevant because for the standard adjustment, there is no global variables. So, I mean, but technically speaking, it quantifies over the initial states of the program. And then, I mean, for both of those, the initial state is the same. But the only place where it plays the role is that we're saying that the leakages on the both sides for both of the cases are the same. And then, I mean, it can start from the arbitrary leakages, and that helps with the compositionality. So, I mean, we start from any state with any leakages, and then we only prove about the extension of this accumulator of leakages.
Hi, so I was wondering if this definition already encompasses the possibility for there to be a small difference between the probabilities of the leakages, because the way that G is quantified, you might have a bit of wiggle room. So I'm wondering whether you considered sort of a computational indistinguishability style definition here.
We didn't.
Okay.
Yeah, but I mean, the important thing is that it's kind of, I mean, I think for different people, maybe either definition 2 or definition 3 is more intuitive of what's actually supposed to be idea behind the leakage freeness for probabilistic programs. And for exactly those definitions, I mean, we show that the equivalence. So, I mean, it's a very fragile property to keep.
Yeah, makes sense. Thank you.
Yeah. Do you have any consideration for like the non-determinate, like if you have a function which is generating randomness,
yes.
But the randomness distribution doesn't depend on the secret? Like, is that covered under this?
Sure. I mean, that's a simpler case. Maybe I misunderstand the question, but
well,
I mean, if your distribution does not depend on the secret input, it's, I mean, we cover even the cases where it will be like, you know, where it will depend in some non-obvious way. But if it's obviously doesn't depend on the secret input, it'll just.
Well, like for the same secret, you might get different values out.
Yes.
But then with a different secret, you also get different values out, but the distribution, like it's not constant time, because it.
Yeah. Here there is nothing about actual. I mean, about the constant time in terms like of the like canonical classical definition of constant time. It's really, I mean, what you're comparing is like at that for this definition, since the program is probabilistic, the leakages are also distributions, which depend on the public inputs and the secret inputs. And then what you're comparing is two different distributions of leakages.
Test.
Perfect. So the second speaker will be Basile Pissin on formally verified hardening of C programs against hardware fault injection.
Thank you. So I will start with defining these terms because they might not be familiar to everyone. So what is a fault injection? Okay. It's a security concept. So let's take a look at this small program. What it does is compare the pins that you entered to unlock, for instance, your phone or maybe your credit card with an expected pin that's stored somewhere in the memory. We assume that the two are the same length. Yeah? Okay. We assume that the two are the same length, and this code should be relative. So at the start, you set an OK flag to 1, and if ever one character differs between the entered and the expected, you set OK to 0, and at the end, you return OK. And so if you're an attacker, of course, what you want to do is to make this function returns OK equals 1, even if you didn't enter the correct pin. So is that possible? Well, actually, if you have physical access to the card, this is possible by using a technique called fault injection, where you typically disrupt the processor using physical means. So it could be glitching its clock signal, or maybe firing a laser at it at a very precise time and place. And this would disrupt the processor, disrupt the execution of well-chosen instruction. And so it could mean skipping this instruction or modifying what it does. In this specific example, what the attacker might want to do is to disrupt the conditional test that's generated by the for loop to invert it. So if you invert it at the first iteration, you will skip the whole loop, you will exit from the loop immediately, and you never do any of the tests inside, so you return OK equals 1 immediately. And you won as the attacker. So of course, for this example, there's a really simple protection against this particular attack. You could just add the test at the very end here that checks that the value of I at the end is indeed equal to pin length. And if it is not, it means something fishy happened during the execution of the loop, and you can exit maybe with an error message. OK, so adding this piece of code here at the end, it's what is called a hello? Yeah. Here I added the countermeasure in the source code, but you process include countermeasures directly in the hardware, or you could also add countermeasures during the compilation to unprotected source code, and that's what we do. And if you do so, there's actually two properties that you might want to prove from these countermeasures. You might want to prove that they are correct in the sense that if there's no fault, adding a countermeasure actually doesn't change the semantics or the behavior of the program that you're protecting. And the second property is that the countermeasure is actually efficient. It does protect from the attack in a certain sense that we will define later. And so we've been working on implementing countermeasures and proving these two properties in the context of the CompCert verified compiler, which is implemented in the ROC interactive theorem prover. So for people who are not very familiar with CompCert, it's a compiler for the C language. It has a bunch of intermediate languages ranging from C to assembly language at the end. But today we'll only focus on one specific intermediate language, RTL, here on the right, which is a language where most of the optimization of CompCert are done and where we also implemented our countermeasures. So RTL looks like this on the bottom. Programs are represented by control flow graphs of instructions. So here the example corresponds to the verify pin function at the top. And you can see that in every node of the control flow graph, you have a single instruction, which could be an operation or assigning a register, or a conditional test. So in particular, here you have two conditional tests. The one on the left corresponds to the for loop, and the one on the right corresponds to the if inside of the for loop. And you have a lot of other kinds of instructions, but today we'll mostly be concerned with operands and conditional tests. OK, and so in this language, we implemented two countermeasures from the literature. The first one is the intra-procedural control flow checking, which was first introduced in a paper called Swift, and later improved for cybersecurity purposes. And so it actually protects against the exact kind of attacks that I described in the introduction, so inverting a conditional test. And the way it works is by essentially doubling the test. Instead of testing once, you do the test twice, and you assume that even if the attacker could invert the test once, it will be more difficult for him or her to invert the test twice in a row, so that's why we consider that it protects effectively. In practice, it's implemented like so. So the idea is to attribute a signature to each basic block in your source program. So here we chose 33 for the block before the test, and 42 and 78 for the blocks after the test. And then you will generate a code that looks like this. So let's detail it. This signature 33, it characterizes at every time the basic block in which the execution is. And so we store it in a special register introduced by this compilation pass, which here is number x1 at the top right here, which we call the general signature register. And then, so you do a pretest, and depending on the result of this pretest, you will assign to another new register x2, which we call the transfer signature, the register transfer signature, value that is composition of the signature of the source block and the signature of the target block where you're supposed to go. And this composition, it's actually just a XOR operation because XOR is very practical, it's easily invertible. Then you go back to the same, to a test, and then you do the test a second time. So indeed, you protect from an attack against a single test because you do it twice. And depending on this test, you will XOR the GSR with, so x1 with x2. And so here on the left, normally, since x1 was equal to 33 at the start, it should now be equal to x2. If it's not, it means something fishy happened. One of the tests was inverted, and we can go into catch, which essentially raises a kind of error message. So you should be convinced that this countermeasure actually protects against inverting a single test somewhere in this. It actually protects against some other kind of attacks, which is quite popular, called return-oriented programming. So without going into too much detail, the idea is to override the return address somewhere in the stack, or at least several return addresses, and to use them to jump around in functions to execute some code that the attacker might be interested in running. And this actually protects from that because if you insert a check of the GSR at the very end of the function, just before a return, it means the attacker that jumps in the middle of a function, this break of the control flow will be detected by the countermeasure. But it doesn't really protect if the attacker jumps at the very start of the function because that's where GSR was initialized. And so to protect against this, we implemented a second version of the countermeasure, which I will not go into too much into detail, but the idea is essentially the same. You have some signatures for each function at the entry point and exit point, and you compose them and you check that you entered the correct function and that you exited from the correct function. Okay, so these are the implementations. We did that in CompCert, and now we want to prove that they are semantically correct in the sense of CompCert. So CompCert comes with an end-to-end correctness proof, which essentially says that the behavior of the target and source program are the same. And this proof is composed of a bunch of simulation proof, one for each compilation pass, that relates the semantics of the source and the target of the compilation pass. And so to explain this more, I need to show you what the semantics looks like. It's a small step semantics, so for every language of CompCert, it's a small step semantics, except maybe for the very source language, but for RTL it is. And so it's a sequence of rewriting steps that will transform a state, so S0, S1, S2, which represent essentially the state of the machine that's executed the code. So for RTL, this state is quite high level. You have a representation of the stack, which is this big sigma here. You have the functions that you're in, F, the program counter, so the identifier of the current instruction to be executed, PC, the set of registers, and the memory of the machine. And for every step, you may or may not see some observable events, which would be maybe writing to a global variable or doing a print or something, which are characterized in this trace T1, T2, T3, etc., etc. And here are two examples of the rules that gives these steps. So the first one is for the operand instruction, just applying an operand from the architecture from the ISA to some registers, and you just evaluate the operand on the values of the argument register. This should give you a value in return. You put it in the destination register, and you jump to the next, to the successor of this operation, which is L. And the second rule is for the conditional instruction. So you have a conditional with a condition, some argument register, and two destination, and one L1 and L2. You evaluate the condition. It should give you a Boolean value B. And then depending on this B, you jump either to L1 or to L2 in the next state of the machine. And so for each pass of concert, you must establish a simulation which shows that the behavior of the source and target program are the same. And usually it's basically building this kind of simulation diagram where you have at left S1 and S2 are states of the source program. At right, S1 prime and S2 prime are state of the target program. And you establish, you write a relation, so it depends of your compilation path, this tilde relation between them. And so you must prove that for any steps in the source program from S1 to S2 with a certain trace, you have a sequence of steps from S1 prime to S2 prime with the same trace, which leads you back into a state that's still related to S2. And in practice, my experience is that the most difficult part of any proof is actually finding this relation. So here is a small example of the relation for our own compilation passes. For the intra-procedural, it's not that complicated. So we say that two states are in relation if their stacks are in relation and their registers are in relation in the following sense. So two sets of registers are in relation if for any register that already appeared in the source program, the values of the register in the target and source program are the same, because we are just adding some new registers. So this part is easy. We will always have the same values for the source registers. And then we also have a register associated to the GSR, which should always be equal to the value of the signature associated with the PC, with the current program counter. And then the relation between sigma and sigma prime is just propagating this kind of relation up the stack frames. So this one is quite easy. For the interprocedural CFC, it's actually far more complicated because of the way we interleave new call to functions, which changes the shape of the stack and the shape of the memory layout at the same time. So we have to use fairly complex system of concert, which is called memory injection, but I will not detail it too much in the presentation. And there's another complexity that we encountered when writing these proofs, which was to reason on the actual syntactic transformation. So let's forget about the semantic for this slide. Let's just look at what our program is syntactically. So our program is a control flow graph, which is expressed in concert essentially as a map from node identifiers to actual instructions. And the way it's transformed, the first version of our transformation, we implemented it using a state monad because Coq is a pure functional language. So whenever we want to do some sort of global state transformation, we need a state monad. And we use it essentially to generate new program counters from new instruction. This is kind of mandatory, and this is what is done in most of compilation passes of concert. But then it's quite tedious to reason with it because the state monad, you make your transformation somehow a bit global, while you would like to reason locally on part of the graph you rewrite. And so instead, we proposed a new framework in concert, which is based on instruction to sequence rewriting. So if tomorrow you want to write a compilation pass in RTL, you might find this framework useful. The idea is that, so if you want to write a new compilation pass, you will just provide some function that says for each type of instruction, how it is rewritten into somehow a sequence of instruction. So here on the left, I wrote it in a textual representation, but we introduced a new AST to represent these sequences of instruction, which may contain some conditional in the middle. And so this is this part in orange is specific to the transformation that you would like to implement. And the part in the bottom in blue is generic. So from this transformation, it actually generates a function that will transform the whole graph. And it gives you a specification which relates the source and target graph transformed, and a proof of this specification. So this automates somehow the reasoning about the graph transformation, and we found it quite practical in practice. Okay, so now let's talk a bit about the robustness proof. I just talked about correctness, but now let's talk about what was most interesting to us. We wanted to characterize that our countermeasures were actually efficient against some attacker models. And to establish that, to prove that in COC, we must first define what is an attacker model in COC. And it's actually not that complex. I said earlier that the behavior of a program was characterized by the sequence of steps with some observable events. Well, a fault is actually a special kind of step with an observable event. Careful, there is a fault here, which you can see on the trace, which will lead us in a new sequence of steps different from the ones that should normally have been taken from the canonical behavior of the program. And so to introduce new attacker models, we just introduced some new rules, some new step rules with these faults. So here is the one for the inversion of a conditional. It's exactly the same as the rule for conditionals that we saw a few slides earlier, except at the end here, L2 and L1 are inverted. And so we define what it means for a program to be attacked, and now we can define what it means for a program to be protected against an attack. It essentially means if ever there's somewhere a fault in our execution, then if we continue to step, if the program continues to execute, it will always end up in a state where the fault has been caught. Special state that we introduce, which essentially means we went to this special catch instructions that I showed in the example. And most importantly, we do this new sequence of steps without doing any observable event. Here's the trace on the bottom. You can see that it's empty, because if there's an observable event on this trace, it means probably the attacker managed to leak some secret or to do something to the machine that we didn't want to happen. There's actually a second case that's a bit more marginal, at least in the example that we showed. You could imagine some fault attacks that don't actually have any real effect. And so you can characterize that by saying, actually, we will return to one of the normal states from the source execution while doing exactly the same trace. And if we're in this case, it's OK. We can also accept this. OK, and so here is the theorem that we want to prove. Proving this theorem means a program is robust against a certain kind of attack. And so the proof for this theorem is actually, the structure of the proof was actually the same for the three attacker models that we described in the paper. So the inversion of conditional and two attackers model for attacks on function calls. But I will just show the example for the intra-procedural, so inversion of conditional from before. As the proof is a bit complex, there's a few complexities. The first is that there's a bit of combinatorial work to be done there, because if you look at this code, actually, you could imagine that the attacker attacks at 3 different points, 4 actually. Every time there's a conditional, you could imagine an attack, so it could be here, it could be here, it could be here, or on the left side. But let's just talk about this case, and the others are treated more or less the same. So now let's imagine the reasoning that we have to do when we are here. What we want to prove is that if this was attacked here, actually the red part should be on the left, sorry. But we actually get into the catch at the end. And so to prove that we actually get to the catch at the end, we must prove that the condition x1 equals 78 evaluates different from 78 evaluates to true. And to prove that, of course, we need to know the value of x1. And to do that, if you look at the instruction just above, we need to know the values of x1 and x2. So the value of x2, we can see it easily. It's just above our fault that we injected here. So it should be easy to recover it. Actually, it's a bit technical because of the way the semantic model is encoded. But we wrote a bunch of reusable lemmas and tactics, and it allows us to do our inversion of the semantic derivation and to recover the value of x2. But for X1, it's more difficult because, as you can see, it's not assigned here in this small local part of the program. It was assigned way earlier. Maybe last time there was a conditional test or at the start of the program. But locally, we cannot find the value of X1. Fortunately, if you remember, in the correctness proof, in the invariant, a few slides earlier, we had the property. We knew what the value of GSR was. It's always equal to the signature associated with the current program counter. And so to recover it, what we needed to do was to propagate the information from the correctness proof to the robustness proof. These are two separate proofs. But to be able to propagate this information, what we did is introduce a new instruction, assert, which encodes that a condition must always be true. If this instruction is the condition x1 equal to 33 here at the top is not true, the program doesn't have a semantic. And so to establish the proof, we prove that this condition is true during the correctness proof. This is trivial because we already have the invariant. And then our local inversion allows us to recover the property. And now we know the value of x1 just by local inversion on the semantic derivation of this piece of code. OK, so that's it for the proof. To reiterate, what we proved is that after the compilation pass that adds the countermeasure, the program is actually protected against the attack model. Now the question is the program at the very end of the compilation chain, the program emitted by CompCert, actually protected against this attack model? This is actually what we're interested about. And the answer is we're not really sure, because in particular, CompCert is an optimizing compiler. It's not the most optimizing compiler, but it does some optimization. And any optimizing compiler could tell you that actually these two conditionals here should always evaluate to the same value. So I can just remove the second one. And our countermeasure is already broken. We already lost. Too bad. This is actually a general problem with people who write countermeasures, even in the source code, to fight against this kind of optimization. So we just wanted to quantify when it actually happened in CompCert. And to do that, we plugged CompCert to Lazar, which is a tool to do some symbolic fault injection on LLVM programs and test if some attack objectives are reached. So I will not go into too much detail in the transformation. But here are the results. So first, one good news. If we turn off the optimization of CompCert and we activate our countermeasures, there's no single fault attack scenarios left when we test with Lazar. There are some two-fault attack scenarios because you can just invert two of the tests in our countermeasures, and it works, but no single fault, and that was our goal, so we're happy about that. But as soon as we activate the optimization of CompCert back, then the one-fault attack come back, at least for some examples. So we managed to fix this issue by following an approach from an earlier paper, which is essentially to opacify a bit the program by adding some opaque copies, which behave as movies in the final executable, but the compiler is not supposed to notice that. And so this allows us to somehow hide from CompCert the fact that there are some redundancies in the countermeasures, and so it doesn't optimize them anymore. And this seems to be working, at least for the few tests that we ran. OK, so to conclude, in our work, we proposed a methodology with a bunch of new interesting tools in CompCert to to implement countermeasures, but also maybe other kind of passes, and to prove the correctness and robustness, which was a real new thing, of these countermeasures. We applied it to two specific countermeasures, mostly focused on control flow checking. But we believe that our methodology could be applied easily to other kind of countermeasures, so instruction counters, load duplication, calculation duplication, etc., etc. If you want to implement one of these countermeasures yourself, because you're interested in these questions, you can find all of the codes online at this pretty long URL. But there are still some interesting questions. And the main one that we are now interested about is what I talked about in the last few slides, the question of end-to-end correctness. So end-to-end robustness. So is the program at the very end of the compilation chain actually protected from fault injection? By testing with Lazar, it seems to be, but we don't have a formal proof of it yet. And of course, this makes us sad. And So there's a question if we could extend our work with opaque copies and somehow formally characterize what these opaque copies do and if it actually protects the countermeasures from optimization. And the end goal would be to have a theorem for each compilation pass in CompCert that says that if the source program is robust, then the target program is robust. And then composing these theorems with the countermeasure robustness theorems would give us a theorem at the end that says the very last program generated by CompCert is robust against this or this scenario. Of course, if we want to prove this theorem for each compilation pass in CompCert, there's a lot of work because there's a lot of compilation pass in CompCert, and there's also a lot of different attack models that we may want to tackle. So there's a problem of combinatorial explosion there. And so there's a question if we can make the proof somehow free by integrating it with a robustness proof, maybe somehow following the approach described in this paper, which was focused on the proof of preservation of the constant time property inside CompCert. But we're not completely sure yet that their approach applies to our work. I mean, to the question of robustness against fault injection. OK, thank you very much, and I'm ready for questions.
Thanks for the talk. I know where some of my friends who I'm going to tell about this are going to ask. So the very first question is, I see you've got you are applying possible state transitions. You're like, what does a fault injection look like? And you're modeling that with like a mapping between states. What about fault injections inside of the program code itself? Do you think this approach would extend to not just the state modifications, but program modifications?
I think in general, you mean some kind of permanent transformations that would change the text of the code itself?
I mean, like in a von Neumann style system where you're possibly modifying the particular instruction that's going to be loaded.
Yeah, but you mean you're not modifying it just during this execution. You're modifying for all time, and if it's in a loop, it will be modified every time the loop.
Yeah, potentially.
Okay. Yeah. It's not completely clear if you could do that with this characterization. I think you would probably need to, if you wanted to use this kind of model to characterize what you just said, I think you would probably need to encode it with some multi-fault. So instead of saying you have a single fault which modifies this instruction, you have, I don't know, n faults which always do the same thing. So that would be probably the only characterization that you could do if you still want to encode your fault injection like this. Otherwise, maybe you could model this actually by injecting the fault on the instructions that call the function, because actually you can see that so the part that tells you which instruction you're about to execute is here. So it's f.code = PC. So you could model this attack by saying, when you jump into the function f, you modify the text of the function f here. So I don't have the rule for the function call in my slides, but it essentially retrieves f from the global context. And so here you could modify it and say, the code of f has been modified.
Thank you.
You're welcome.
So I was wondering about this plan that you sort of described at the end for like robustness preserving compilation. I'm pretty sure that most of the current passes of CompCert are not robustness preserving. Is there evidence that like this is actually a feasible strategy for building a compiler to begin with? Like, are there compilers that are robustness preserving, or at least seem like they would be, such that attempting to prove it is not completely unreasonable because the theorem's false?
Okay, so first it depends of your definition of robustness, of course, which is parameterized by which attacker model you actually consider. So the answer is it depends also what you define as a compiler. For me, a compiler is a sequence of paths, so I could say compsert -O0 is a compiler that's robustness preserving for some compilation passes. But yeah, the point the problem that you point to is real. Compsert is not robustness preserving. We saw it when we ran our experiment, the question is, the question now is what we would like to prove. The real result is compsert with inserted opaque copies robustness preserving, if we insert them in the right place. That might be true, because, I mean, experimentally, this is true for these 4 programs. That might be true in general. We don't have the proof. That's what we want to get. So that's what we want to prove. And so, as I said in the last slide, the most relevant previous work is this work, but it was on it was focused on the preservation of the constant time property. And so in this work, there's a really nice, not trick, but encoding, where they encode the leaks as observable events, a bit like we encode fault as observable events. And they use that to say, transformation passes preserve the trace, including the leaks, or remove some leaks. And so this means that the leaks, the compilation is leak preserving, so it's constant time preserving, essentially. It doesn't add any new leaks. But it's not clear to me that, so even if we encode as the same way as encode leaks as observable events, we encode faults as observable events, it's not clear to me that the same strategy applies for faults, because for faults, you essentially quantify on executions, and I don't think that's exactly the case in this article. But yeah.
I would also have a question regarding robust preserving compilation. So this robust preservingness, did you prove that for your own transformation, that you can iteratively apply that? You say if you apply it once, then you have a fault tolerance of at least 1 fault injection, and if I apply it another time, then I just add 1 more number.
No, I didn't, because we didn't give a specification. So that's the implied question in your question. We didn't give a specification of multi-fault attacks. Our robustness theorem here, it only works for single fault attacks. And so we haven't written yet the version for multi-fault attacks, but we believe that it would be more complicated because you need somehow to count the attacks, and you have some combinatorial which says when did one fault occur, when did the next one occur. So we didn't give this definition, and therefore we couldn't prove what you proposed. And I think the proof would probably be quite complicated, but I haven't thought about it in detail. So.
Okay, so let's take the other questions on offline, and let's go to our 3rd talk, which is an online talk, I think. Wait a moment for this. Okay, so the last talk will be online with Wolf, who will talk to us about certicog-wasm.
Yeah, welcome everybody. Thanks for joining the presentation of our project, certicog-wasm. So in one slide, our project is about compiling Coq code to WebAssembly in a verified way. So imagine you have developed a program in the Coq proof assistant. That is, you wrote a program in its Galena language and proved that it adheres to some specification. Now you want to integrate that into a real-world application that may be written in a language like C or OCaml. So what you want to do is you want to extract your Galena code to such a language. Now, Coq comes with an extraction to OCaml, and other projects target other languages, including C. But in this project, instead of languages like that, we want to target WebAssembly. And what this will allow you to do is that you can run your Coq programs on the web. And that is because modern web browsers like Chrome or Firefox come with a runtime for WebAssembly programs to accompany JavaScript programs. Now, while WebAssembly is gaining popularity in other use cases as well, if you're not yet familiar with WebAssembly, a good way to think about our project is that it allows you to run Coq programs on the web. And then as a second point, our transformation is verified, because if you took all this time and effort to verify your Coq program, you don't want that the extraction mechanism introduces a bug. So given that the extraction mechanism is verified, you can be quite certain that the produced program does what you originally, that it does behave in the same way as the original program, right? As part of this presentation, I would like to convince you that our tool is practical and useful in practice. So we built a little demo application where we built a little website that allows you to compute the SHA-256 sum of an arbitrary input string. So we took an implementation of SHA-256 that's developed and proven correct in Coq and extracted it using our tool certicoq-wasm to a WebAssembly binary. And then we wrote a little bit of JavaScript to write this little user interface around it. And then you can input a string, and our certicoq-wasm tool produces the same result as the standard browser API. So in the remaining presentation, I'll talk about how it works, how it compares to other ways of extracting to WebAssembly, and then we have another practical application. I'll start with an introduction to WebAssembly in case you're not familiar with WebAssembly. So, as I've already mentioned, it's supported by the major web browsers. And this is cool because you can now use your favorite programming language to develop web applications. But also outside the web browser, there's WebAssembly is gaining a lot of traction, in particular in blockchain applications, in edge computing, but there are really many other applications, and people are really excited about it. And the reason people are getting excited about it is because the WebAssembly specification defines a secure sandbox that has fairly simple and clear semantics. And you also, in addition to the security property, you also get binaries that run fast. And in our case, WebAssembly, what's useful for our purposes is the WebAssembly mechanization. There exists one in Isabelle and Coq, and our work is developed in the Coq proof assistant, so we depend on this wasm-cert project. WebAssembly programs are organized around modules. So this is a very simple example module that has two entities. So there's a global variable that's initialized with 41, and then there's a function that adds 1 to this global. And given that WebAssembly has the sandbox property, only the exported add function is visible to the runtime, but the global, for example, is not visible. You would have to mark it as exported explicitly. A word on the a word on WebAssembly's operational semantics. So the host runtime has its own state, but since the binaries regenerate do not interact with the host runtime, that stays the same, so we omit it. And what's of most interest to us is the store and the frame. And these two capture the state of the machine during execution. So the store captures the global state of the execution, mainly the current values of global variables and the current contents of the WebAssembly's linear memory. And then the frame contains, it's a function local stack frame, contains the current values of the local variables. And then we have a set of instructions, list of instructions. So just to give you a sense of what it's like to step through a WebAssembly program, this is the program from just before, and you can see the configuration, the start configuration at the top. So initially there's the value 1 on the stack, and then as in the first step, the machine executes this global.get, which initially has the value 41. So the two values 1 and 41 on the stack, these are then added, and finally the global is updated with the new value, resulting in a new store S prime here. Now some background on Certicock and the lambda-NF intermediate language. So as the name of our paper suggests, our work builds on Certicock, and in this figure I'm showing you a simplified version of the Certicock pipeline. So Certicock comes as a Cock plugin, so we start at the top with the original Galena program. That is then reified into the Cock AST that is part of the MetaCock project, and then follow various steps, various transformations with various intermediate languages that I summarize here as Certicock core. This includes some optimizations on the lambda-NF level as well. And finally, Certicock generates C code from this final lambda-NF language. Now, all of these steps are verified. For one or two of them, the verification is a work in progress, but once they're done, you get a compiler that has an end-to-end correctness statement. And instead of generating C code, we insert our backend here right after this lambda-NF intermediate language and generate WebAssembly code from this intermediate language. So what does lambda-NF look like? Lambda-NF is an untyped lambda calculus in a normal form. I will start with the values. So in lambda-NF, there are three kinds of values. There's constructor values, there's function values, and there's primitive values. In our case, primitive values means 63-bit primitive integer values. And then you have various expression types. So you have constructors, you have projection to access constructor arguments, you have a case distinction, then you have function definitions and function calls, And then you have primitive values and operations. And these primitive values and operations correspond directly to the ones that are available in COG itself. So in COG, to enhance performance, you can use primitive integers and operations and floats, and I think also arrays. We currently only support primitive integers, and we support all the 24 operations on them. Think like arithmetic and logical operations. So this is what a typical lambda-NF program looks like. This is the program you get when you compile the COG term length of the singleton list. It contains just 0. And what's notable here is that you get a top-level set of function definitions. And this set of function definitions is followed by the main expression. The fact that function definitions only occur at the top is ensured by a previous optimization on lambda-NF in the previous 30-COG pipeline. And the fact that function definitions only occur at the top makes it easy because we can translate, because we can convert them one by one to a WebAssembly function in the final WASM module. And the main expression, we translate that as well and place it in a main function in the final WASM binary. So now I talk about how our backend works. So we have a top-level compilation function that takes a lambda-NF expression of the form that I've just shown you, and it produces a WebAssembly module. This module has a WASM function for every lambda-NF function and a main function containing the main expression. And then it has various other entities, such as a linear memory, which is used to store constructor values and primitive values. And then we have a bunch of globals and other entities. Second, we have the codegen function, which takes lambda-NF expressions as well. And this is the function that actually produces WASM code. So this will return a list of WASM instructions, and these are placed in the WASM functions as a function body. The WASM binaries we generate use a simple memory model without garbage collection. So what happens is that whenever we allocate a value in the linear memory, we preserve a high watermark, so to speak, and this ensures that old values are never overwritten, but we just write a value to the next free space in this linear memory. And given that the WASM linear memory is limited to 2 GB, if we need more, then we terminate with the out-of-mem flag set to 1. So there's a limit to the size of programs we can run. But as we'll see in the evaluation, this is not, for our set of benchmarks, this is not a limitation in practice. So how does this codegen function work? The main consideration here is how do we represent lambda-NF values in WebAssembly? And for that, we choose a representation that is quite similar to, or very similar to, the one used in 30-COG C backend, which in turn is essentially the same as the representation the OCaml compiler uses. So we represent lambda-NF values as I32 integers, and recall that there are 3 kinds of lambda-NF values. Function values are represented by the index of the corresponding function. Primitive values are boxed in the linear memory. And then we have constructor values. Non-nullary constructors are also boxed in the linear memory. And That is essentially a pointer pointing to a segment holding the constructor tag, followed by the arguments. And then that is not necessary for nullary constructors, which we can just identify by the tag. We shift it to the left, add 1, so we can distinguish the two constructor types. This brings me to the correctness statement we proved about our backend, and I'll just go through it. So we have a top level lambda NF expression that has some function definitions, and if you evaluate this expression in the empty environment, you get a value v. And finally, there's if you compile this lambda NF expression with our backend, certicock wasm, you get a wasm module. Now, given these, it holds that the module instantiates through an initial store and frame. Instantiation in WebAssembly context means transformation to the original runtime representation. And this only succeeds that when the module is well typed. So this includes the proof that modules generated by certicock wasm are well typed. And when you call the main function on this initial configuration, you're left with a final store SR prime that has which the global variable result has the correct value set. And this here is just the value relation I've shown you just before. Or as another option, we ran out of memory. That's also okay. The proof is a forward simulation over the evaluation derivation, and you're welcome to check the paper for the details. This is a visualization of the proof, and I'll just explain it on a very high level. So as before, we have the initial lambda NF expression that is evaluated on an empty environment to a value v. Lambda NF expression is compiled to a module, then it holds that it instantiates, and if you call the main function, you're left with this final store SR prime, for which the result variable is set correctly. And this is ensured by another relation that links the lambda NF environment to this pair of store and frame throughout the execution to ensure that whenever an evaluation step is taken on the left side, the same behavior is simulated on the bottom side. This brings me to the evaluation. So we choose a set of benchmarks that include the certicock benchmark suite. These are mostly some micro benchmarks, but also more complicated, computationally expensive benchmarks. And then we choose some of our own. So we choose the Ackermann function, we include the Ackermann function, and we include a benchmark cock prime. And what's special about the last benchmark is that the cock program uses cock 63-bit primitive integers and operations. Since we're not aware of other extractions that directly target WebAssembly, we combine various extractions via intermediate languages. So we have an extraction via C, via Rust, via OCaml, and via mel function. Mel function is a wrap around one of the OCaml compiler's intermediate languages. And then we combine these extractions with off-the-shelf tools. So this is mscripten, which is a very popular tool to compile C-like languages to WebAssembly. This is just the Rust compiler, and we have this wasm of OCaml tool. This is our work, and once the remaining stages are verified, this gives us the first extraction to WebAssembly that has an end-to-end correctness statement. Whereas the others, you have to just these programs, and the two on the left, for example, include all of the LLVM infrastructure in the trusted computing base. Now, to be a little more precise, all of these extractions target different versions of WebAssembly. So WASM 1.0 is the original standard as it was defined in 2019, but that standard has been evolving and was extended with multiple proposals. The one we target includes the tail call proposal. So in WASM, you have to want a tail call. There's a specific instruction for that, which we make use of. And then there's a further proposal, the WASM GC proposal, which adds garbage collected reference types to WebAssembly. So you get heap allocated structs and arrays for which the runtime is responsible for garbage collection. Now you can see that these are not exactly perfect to compare, but that's what we've got. So this is the performance comparison of our tools. I'll start with the failure. So our tool is the only extraction that generates a WASM binary that computes the correct result for all our benchmarks. And the other extractions either produce ill-typed code, like the first two here, or they don't support or they don't support the 63-bit primitive integer operations, as is the case with the Rust and the mel function extraction. So for these two, the compiler just refuses to compile the input program. And then the extraction via C produces a binary that crashes when you run it. Now, in terms of performance, we use all the other extractions in the production settings. So with all optimizations turned on, and then we have our tool without optimizations, and also with optimizations provided by the WASM op tool, which is a popular WASM optimizer that's used a lot in the WASM ecosystem. And then we have a prototype that also targets this WASM GC version, but that's an unverified prototype. So what you can see here is that compared to Rust or C, our 30-clock WASM produces code that performs quite a bit better, that's faster. And compared to OCaml and mel function, we're roughly equal. So we're a little worse than the extraction via OCaml, and we're roughly equal to the one via mel function. But keep in mind that the OCaml mel function extractions target this other version of WebAssembly. Yeah, and then our prototype is quite a bit worse. In terms of the binary size, so above in the upper half, we have the ones that target WASM 1.0. And for these, our tool generates the smallest binaries, except for the color benchmark, where the Rust one is better. But compared to the C1, we generate significantly smaller binaries. And the reason for that is that the C extraction includes a garbage collector written in C that is verified and written in C. And from another perspective, you could say that well, with the extraction via C, you could run larger programs, but at the cost of having larger binaries. And for the ones that target WASM GC, we have It depends on the concrete benchmark. So we are worse for some and better for some of the benchmarks. I skip to the conclusion. So we presented a verified WASM backend for Certicog that significantly reduces the trusted computing base when extracting from Berliner to WebAssembly. We believe that it's fast enough and that the binaries are small enough for it to be practical, and we support the translation of primitive 63-bit integers and the operations on them, which most of the other extraction tools do not support. In the future, we also want to look at optimizations on the WASM level, WASM opt but verified. And if you're interested in that topic, please reach out to me. With that, I thank you for your attention, and I'll happily take some questions now.
Thanks. We still have time for 1 or 2 questions. Okay, I have a... Oh.
Hi, thanks for the talk. So in the malfunction setting, there is also a theorem about realizability semantics, the fact that we characterize the kind of, at which type we can guarantee a bit more about the function, just the execution, but also the interaction with the malfunction external world. Can you think about a kind of corresponding theorem in WebAssembly characterizing over which type of the function you can guarantee that the interaction with other WebAssembly codes can be safe? Does the question make sense for you?
I think you're referring to foreign function calls, is that right?
Yeah, for example.
Yeah, so there's a different project that adds a verified function interface to Certicog, and there's going to be a talk about this tomorrow, I think, called VeriFFI, and they present a verified foreign function interface, I think originally planned for Certicog C backend, but as far as I know, it should also be possible to make this work for WebAssembly. I've been told that it's generic and one should be able to make use of that.
Okay, thanks.
On slide 22, you showed the very poor performance with the garbage collector. Could you explain why this happens? Like it was in your prototype, I think, which you said.
You mean for the Cog Prime one?
Yes. What makes the garbage project, like what makes the version with the garbage collector so much worse? Do you know, or?
Yeah, so each 63-bit primitive integer is boxed in a struct, and in my opinion, this leads to a lot of memory accesses and storing values to the heap, because you have to always box and unbox these values, and because there are so many primitive operations, this happens quite a lot, and this does not happen with the other benchmarks. But I would like to say that this is sort of a prototype version, and I think it could be optimized if we spend some more time on it.
Okay, if there are no more questions, let's thank all 3 speakers again.
Okay, then we can get started. Yeah, so Mircea Seve is going to tell us about nominal matching logic.
Fixed point binder, which is quite crucial to our current work. It's also the foundation of the K framework, for those of you who are familiar with the K framework. If not, I'll just mention that it's a framework for defining semantics of programming languages. And being the foundation of K, we can effectively express all of the semantics in matching logic, which is why it makes it appealing as a target for formalization. And it's also very simple and very general, allowing us to embed many other logics using verification in it. So to get a bit more familiar with matching logic, I want to talk about patterns, which are effectively the formulas in matching logic. We call them patterns because semantically they match a whole set of elements rather than just one element in the universe. So you can think of it kind of like a model logic, but one of the main advantages that this allows us, of this approach, of this logic, is that it allows us to express both terms and propositions pretty much homogeneously at the same level. So for instance, you can have patterns such as this crazy one right here, which is f applied to an existential. And under the existential, we can have a term, which is successor of x, and then a predicate is even, that's applied to x. So semantically, when you want to talk about the truth value of a proposition like it's even, it's going to be true when it matches the whole universe of objects semantically, or nothing. So in this case, if something is even, if x is even in this case, it will match the entire universe of objects, and the conjunction is interpreted as set intersection, and successor of x is interpreted as just a singleton object. So if we're looking at an x that is even, this is effectively going to be successor of that x intersected with the whole universe, which is still the successor of x. And then the semantics of existential is effectively we take all possible x's and we take the union of all of these sets. So it may be a bit confusing to think about this right now, but what this is going to match is effectively f1, f3, and f5, all the way to infinity, f of any odd number. A signature of matching logic theory consists of tuple S, EVAR, SVAR, and sigma, which is made up of sorts, element variables, set variables, and symbols. This is all we need to construct patterns. And once we fix this signature, we have the following grammar, which allows us to build patterns, which is on purpose chosen to be as minimal as possible. So we can have a small x, so we can have an element variable, which is always going to match a singleton element. We can have set variables named as such because they can match a set of elements. We can have a symbol in our signature applied to other patterns. Then we have implication and bottom, which allows us to do propositional reasoning. Existentials, which allows us to do first order reasoning, and then the mu operator, which is used for fixed point reasoning. So just to give you an idea of the power of matching logic, we can effectively embed all of these logics in matching logic. So that includes Hoare logic, reachability logic, first order logic. We think pretty much everything that you might be interested in. That's the power of matching logic. And this is where our current work fits into the picture. So the previous work that I mentioned, which is nominal logic and matching logic without the fixed points, that's from 2022 by Cheney and Fernandez. And our current work builds off of that. And it can all be expressed in matching logic. So matching logic also has a proof system, which I blur this out because I don't want to get into the weeds of it. It's effectively got a set of axioms for propositional logic reasoning, just what you would expect, 2 axioms for first order logic, 3 axioms for symbol application and propagating logical constructs to symbols, some 2 technical axioms. We don't worry about that for now. And then we have the fixed point axioms, which are quite important for the technique that we're going to be illustrating. So the H fragment of the proof system, that's sound and complete, whereas H mu is just sound. And I want to also mention applicative matching logic, which is a variant of matching logic that's more suited for mechanization. It's like matching logic stripped down to the bare essentials. It's just as expressive as regular matching logic. One of the main differences is that it lacks sorts and symbols, singularity and signature information. So all you have is this set of symbols, and you have a binary operator called application, and you can apply a symbol to anything. And this is how you build symbol application. I'm only mentioning this because this is what we use in the formalization, which makes things easier, but not knowing this might make reading it a bit hard to understand, so just to be aware. We effectively can bring back sorts into the picture by formalizing them as a theory in applicative matching logic. I also want to talk a bit about nominal logic, introduced by Pitts in 2003. It's a first-order logic like matching logic. It was mainly designed in order to reason about languages with binders. So it has built-in constructs like abstraction, which we denote by this square brackets notation. We have freshness, saying that a certain atom is fresh in a term. And then we have support of a term, which is the set of, effectively a set of free variables in that term. And it also provides an axiomatization of alpha equivalence. It has a built-in swap symbol, which is at the base of everything. And the semantics are based on nominal sets, which you can think of terms, you can think of them as terms with nameless representations, because we want to abstract away bound names. This is what the axiomatization of nominal logic looks like. I don't want to dwell too much on this. You can have a look at this in your own time, make sure that it makes sense, but it effectively enforces the semantics that we want. I want to talk a bit about our previous work, which is about combining nominal logic and matching logic before we worried about fixed points. So the main point of that work was to leverage the power of matching logic as a very general logic that's used to reason about programs, and nominal logic, which has all of these useful constructs for reasoning about binders. And there were two approaches that were proposed in that paper. We have nominal matching logic, which is an extension of matching logic with nominal constructs. And we have nominal logic in matching logic, where we define nominal logic just as a theory in matching logic without changing the base logic. And this is what we used in our current work. We didn't want to change the base logic. We want to try and do everything in raw matching logic without changing things too much. And the nominal logic axioms, as I mentioned, are also first order. So they translate somewhat naturally into matching logic with a few caveats that I'll describe later. As I mentioned before, a significant drawback of this previous work was that we didn't have any fixed point or inductive reasoning. So we couldn't prove, we could prove interesting things, but only by assuming induction principles as axioms. I want to talk a bit about induction principles in matching logic. So this was touched upon in a previous paper by Chen and Roshu. Effectively, by having the fixed point operator in matching logic, this allows us to define any algebraic data type. So we don't need any additional machinery in our logic, in matching logic. We can just use the mu operator to define effectively any algebraic data type that's recursive. And a cool thing about this is that we can derive induction principles for it. And I'm going to show you a quick examples involving natural numbers in a second. And yeah, we can do proofs by induction by using this technique. So all that we need is these two axioms, which tell us how we can manipulate the mu operator when we see it. One is called prefix point, and one is called Naster-Tarski, after the famous theorem that tells us that the fixed point does eventually converge if certain conditions are met. And here's what it looks like for natural numbers, just to give you a bit of intuition. So if you have a symbol net that you want to stand for all of natural numbers, you can axiomatize this with just these three axioms. So you can say that net is equal to mu x, the least fixed point of this operation. And on the right-hand side, you have successor of x and 0. And the intuitive way to think about what this fixed point operator is doing is to start off with an empty set, assume capital X is an empty set, and then plug it in, you get a certain set, and then you plug it in again, and you plug it in until you get to a fixed point. So in this case, what you end up with is 0 and successor of 0 and successor of 0, and you get all the natural numbers. And the other two axioms are there just to ensure injectivity. No successor of x is equal to 0, and successor is injective. And if we have this definition, we are able to prove this induction principle for natural numbers, which says that if P is a predicate, let's say P is some pattern that matches some elements that we want to be true for that predicate. That's the idiomatic way to do things in matching logic. If 0 satisfies this predicate or is in this predicate, and if the predicate is closed under successor, then all of natural numbers are going to be in our predicate. And now we're going to talk a bit about the current work, the current contribution, which is expressing nominal logic in matching logic with fixed points. Our goal is to bring inductive proofs to languages with binders and to make more rigorous the use of induction principles to reason about languages with binders. We want to be able to derive everything from first principles rather than just assume some structure and assume that we have this induction principle for it, which could have bugs. Now it's just a theorem. And then we can use those induction principles to prove useful facts about our language. And those facts, as we have shown in this work, can be formally proved inside a proof assistant, such as MetaMath0. But the same technique would probably be generalized to other proof assistants. So this is, on the right-hand side, what the analog for the previous axiom that we saw earlier is in terms of lambda calculus. So EXP is the sort of expressions, lambda expressions. And then we use, again, the fixed point operator to describe our algebraic data type. So we have variables. We have application. We want to say that this set is closed under application, and it's also closed under lambda abstraction. And here on the bottom is the induction principle, which we have proved. It's pretty much identical to the one for natural numbers. And this is what these two look like in code, if you are interested. This is a MetaMath0 code. So the no junk axiom, as we call it, is pretty much exactly what I described earlier. You can see that we have the mu operator, we have variables, lambda abstraction. And the lambda case is quite interesting because it uses internally, it has this LC lam, which is just a tag. And underneath, it has this abstraction object that comes from nominal logic. So we have to use, every time we want to define a sort of binding construct in our language, you have to use this abstraction that's coming from nominal logic, so that allows us to actually use the axioms of nominal logic to reason about it. And then this induction principle is the one we proved. It's relatively straightforward to prove this. I'm not going to go into the weeds of it. It's pretty much exactly what we had before, except for the fact that at the beginning we assume that EXP pred, as we call it, the predicate over expressions, is an expression, and which is why at the end we have equality rather than just implication. But otherwise, it's exactly what you would expect it to be. This is another real example of what our nominal theory looks like in matching logic for lambda calculus. I know it's a huge wall of text. I don't expect you to understand what's here. This is just to give you an idea of what it looks like. So the idea is that we, for each of the constructs, for each of the build the constructors of lambda calculus. We define it as a symbol in matching logic. We have an axiom that gives it its arity. As I mentioned before, we work in applicative matching logic, so we need to do this. And then we have another axiom for equivariance. And I will talk a bit more about this later. And this is one of the main theorems that we proved, that we used the induction principle for. And this is a common identity about substitution in lambda calculus. I know it looks like, again, a bit of a wall of text, but if you actually sit down to look at this, what it's effectively saying is that if we are given two different atoms, A and B, and lambda terms P, P1, and P2 with A fresh in P2, we can prove this common identity about substitution. It's just pushing a substitution in through another substitution. And this was entirely proved out of the axioms of matching logic and the axiom that we saw earlier with a mu, with a least fixed point binder. Now we're going to talk a bit about formalization. I have no idea how much time I have left, but anyway, I'm going to try to be quick. So we chose MetaMath0 for a number of reasons. First of all, MetaMath0 is a relatively new proof assistant. It was developed by Mario Carnero as an alternative to MetaMath. It's got an extremely small trust base, which is why it was quite attractive to us to begin with. Probably the smallest. Maybe the other contender would be MetaMath, but even then it's smaller than MetaMath in certain implementations. It's got native support for notations, unlike MetaMath. It's faster than MetaMath. It's got modern tooling, so it was quite nice to work with. And also we chose this because we had some expertise in the team already. We had a library that was already developed for matching logic in MetaMath0 priorly for another project. So we wanted to see how far we can take this formalization. I'm going to talk a bit about the main challenges of these formalizations and design decisions. One of the main challenges was working with a new proof assistant, which takes a bit of time to learn, but once you get used to it, it's not horribly hard, and I want to thank Mario for his support in getting familiar with the syntax and everything. Another technical challenge was figuring out exactly what we want the induction principle for lambda calculus to look like. If you look at the earlier paper, and also if you look at the formalization of nominal logic in nominal Isabelle, you will see that the induction principle for lambda calculus is a little bit different. One of the key differences, and this is what we started off trying to implement, but we ran into some issues. So the difference is in this requirement here in the third antecedent of the induction principle. So this is effectively saying that for the lambda case, we only have to prove the lambda case for certain, for only some atoms, not all atoms, which makes it easier for the user to use this induction principle, but makes it very hard for us to actually prove it. We tried to prove it. We ran into a lot of issues, so we figured out a different approach to do this. And the different approach is we dropped this requirement. We used the standard induction principle that comes from, that's exactly as we did for natural numbers. And then we use that instead. And we don't really need to worry about this. It's effectively a shorthand. It's effectively something to make the life of the user easier, but the user doesn't necessarily need that. And a lot of the times we found that it doesn't really add much. Another important decision that we had to make when designing this formalization was with respect to equivariance axioms. So for those of you familiar with matching with nominal logic, in nominal logic, do I still have time? All right. In nominal logic, every single symbol is equivariant in the sense that if you have a swap operation, swap of AB applied to a symbol and some arguments, the swap symbol is propagated to the arguments. And that is just one axiom in nominal logic. But for this formalization, we decided that instead of having this one axiom for every single symbol, we have a separate axiom for each symbol that we want to introduce. And that's to make it compatible with other theories. Maybe you want to have theories where you don't want to have equivariance for your symbol. So we don't want to force everyone using our theory to have every single symbol be equivariant. So whenever we add a symbol, we also add an axiom that says that the swap operation can be propagated through the symbol. We have one for variables. We have one for lambda abstractions. And if you look at the last line of these snippets of code, you can see that there's nothing particularly interesting going on. But we need these axioms. Another important caveat that I touched on during the presentation is that when you're working in a matching logic setting, as I said, patterns are multi-valued in the semantics, whereas in nominal logic, in an axiom, every single occurrence of a variable is a singleton. So if you naively translate the nominal logic axioms into matching logic without thinking really hard about whether something can be multi-valued or not, you run into problems that are caused by inconsistencies. So your axiom can just can be unsound because of that. So we had to make sure that in axioms such as A1, some variables are element variables, which forces them to be singletons, and some variables are meta variables. So just any pattern, so they can actually be multi-valued. So this is, in a way, another part of our contribution. It's trying to rewrite these nominal logic axioms in a way that's faithful to the original. It's idiomatic to matching logic, so as to allow as many things to be multivalued as possible, but also correct with respect to nominal logic. Right. And then another important challenge in the formalization was restricting the axiom F4, which you might know as the axiom that says you can always find a fresh atom for a set of atoms. In nominal logic, we force this set to be finite so that we can always find a new atom that's different from what's already in the set. But here, it's quite hard in matching logic to say that something is finite. You have to define natural numbers. You have to do all kinds of things to express finiteness. So instead, what we decided to do, and that turned out to be good enough, is to force this set for which we want to find a fresh atom. We want to restrict it to a singleton, to effectively just one atom, or a finite set of atoms that we can build by using a certain special operator that we added specifically for this purpose. I mean, this is a very technical thing. I don't want to bore you too much with this, but the main point I want to make is that things often don't go exactly as you plan when you have to actually sit down and formalize something in a proof assistant. And I want to talk a bit about the future work. As I mentioned before, this is a proof of concept of our approach. We want to prove a bit more facts about lambda calculus, more interesting theorems. We want to adapt this technique to other, hopefully more complex languages. We don't expect there will be any major blocker. We just didn't get around to do this for this paper. We want to find a way to simplify the proofs, streamline them, and maybe develop some meta theorems, some programs that allow us to build these proofs easier. Because this is a new proof assistant and I was effectively working alone, a lot of things took a lot of time, a lot of very simple things, but we hope that we can make things much more streamlined in the future. And we want to make also prove that this embedding of the nominal logic axioms that we chose is faithful to the original semantics of nominal logic. At the moment, for our current work, we just translated them as best as we could and as it made sense to us for this work. So yeah, that's pretty much it. If you have any questions, I will be happy to take any questions. How did I do with time? All good? Thank you.
Any questions? So I have a question. You mentioned that one of your main theorems here was the substitution theorem for lambda calculus, right?
Yeah.
Do you know, I guess one of the selling points of like nominal logic is that, it allows you to prove the substitution stuff only once, and then you can, sort of instantiate it into anything that has binders or whatever. So can you do something similar here? Do you know whether it's possible to abstract this into a version which would save you the time?
Yeah. So that's the main idea. This technique can be generalized to any language. Probably not this exact theorem, because this exact theorem uses constructors specific to lambda calculus. But any extension to lambda calculus can also use this theorem. And if you want to have another language, yeah, I think this should generalize quite easily. That's the idea.
So you mentioned that you have to be careful in the way you state the axioms in order to not reach inconsistency. But I didn't get, how do you make sure that you don't reach inconsistency?
Yeah, so for, oops, sorry. For this, we don't really have a way to make sure about that. I mean, we have a pen and paper proof that's still a work in progress, and it's looking quite good, but we haven't published that yet. And looking at it, we also made sure we also used our expertise to make sure that things make sense, but the actual formal proof is still in progress right now.
Okay, so let's thank the speaker.
Thank you.
This seems to work, right? Okay, nice. Then let me just set up the actual slides.
Okay. Yeah. So our next speaker is Jannis Lindberg, who's going to tell us about ESOP and tactic optimization, I guess.
Thank you very much for the introduction. I'll talk about tactic script optimization for ESOP. And let me first demystify the last word in the title here. So ESOP is a tactic for customizable proof search in Lean 4. It's quite similar to Auto in ROC/COC, also similar to Auto in Isabelle, actually more similar to the Isabelle version, etc. So it applies user-specified rules to goals. If a rule doesn't fully solve a goal, the rule produces some sub-goals. ESOP is called recursively on the sub-goals until hopefully at some point there are no goals anymore. And the rules are really arbitrary tactics, although we provide some syntactic sugar to register particular theorems as rules. But under the hood, we're dealing with arbitrary tactics here. And all of this was presented 2 years ago by myself and Esther, who happens to have the next talk in this session. All right, so the topic of this talk will be tactic script generation. So here we have, as an example, some theorem that says that the head of the concatenation of two lists is the head of the first list, provided that the first list is not empty. And with a little bit of help from this rule that we add here, ESOP is able to solve this. And then we can use the variant ESOP question mark, which allows us to basically replace ESOP with an automatically generated script, right? And the script is essentially generated by ESOP taking the rules, turning them into tactics, which is relatively easy because an ESOP rule under the hood is very similar to a tactic, and then printing them to get this kind of script. However, if we do this naively, it doesn't look quite as nice as we have here on the right-hand side. It looks more like on the left-hand side. So it's a script that works and solves the goal, but is very, very ugly in a couple of ways. First of all, it's just a list of tactics with no structure, whereas here, we have these combinators like next that allow us to focus on particular goals and to say, okay, so for example, this subproof all pertains to the goal that we focused up here. And second, tactics are sometimes applied out of order. So this on goal 2 here means that we apply the tactic to the second goal in the current list of goals. That's quite unnatural when you write proofs as a human, right? You usually just want to attack the first goal until it's gone, and only then do you switch to the next goal. So it's a bit annoying. And there are all these simp-alls. I don't want to get into the details of why, but basically these simp-all calls, if you have them in the middle of a proof, are a big no-no in lean land because they are quite unpredictable. They depend on some global state. If the global state changes, the simp call does something different than before, your proof breaks, and you get unhappy. So therefore, in the middle of a proof, we prefer the simp-all only form, which essentially kind of removes the dependency on the global state. So that's an optimization that we would also like to make. Now, what I basically did in order to fix all these issues is
to write a script optimizer. So a little program that takes the naive script, turns it into the optimized script. And this talk is going to be about how exactly I did this. But first, maybe a little bit of motivation or additional motivation about why we want to optimize. So here are a few use cases where this is useful. First, the most common use case is we might want to replace ASOP with the generated script for performance. Right? Because ASOP does a bunch of search, it tries a lot of tactics, which may or may not take a while depending on how fast these tactics are. Sometimes they're quite slow. And so using the generated script, of course, cuts down on all the tactics that we tried during the search that didn't actually lead to a proof. So it can substantially increase the performance of the generated script. But here we want an optimized script because we don't want to PR this kind of garbage here to Mathlib, because the Mathlib maintainers will shout at us that this is unacceptable. Then you can also let ASOP generate a proof stub. So even if ASOP doesn't manage to prove a goal, it can still usually make some progress using so-called safe rules, which are always good to apply. And then ASOP basically gives control back to you and says, OK, now let's prove the rest. But in that case, so if you use this methodology, you probably also want to replace ASOP with the generated proof stub. And finally, the scripts can help you learn about how ASOP proved a goal, either for debugging or this is a kind of funny use case. So recently, a lean user, newish lean user, talked to me and said he had learned some lean by running ASOP on simple goals and looking at the scripts that it generated, which taught him about some of the kind of basic tactics that we use in lean to prove stuff. Not a use case I was anticipating, but I was quite happy to hear about this. OK. And looking a little bit further into the future, script optimization is not only useful for ASOP, and in fact, the current implementation is only coupled very loosely to ASOP. It's also useful for AI. Right? We're seeing a lot of these AI-based systems that generate tactic-based proofs, and these sometimes already contain some sort of post-processing that's quite similar to what I'm doing, because the proofs generated by these AIs usually tend to include a bunch of garbage that doesn't actually contribute anything. So they need to be post-processed in some ways. And thinking even further into the future, I think it would be nice if eventually we as humans could just write a proof in whatever kind of way we want, being kind of as dirty as we like, and have an optimizer clean up after us. This would bring us into the realm of sort of auto-formatting tools for programming languages, stuff like that. OK. For now, let's kind of stay in the present and stay with what I actually implemented. So I implemented a script optimization pipeline with 3 steps. And I want to talk to you about the first 2 steps. The first step is what I call local dynamic optimization. This is where we take single tactics, that's why I call it local, and we optimize them, and then we check whether the optimized version actually behaves the same as the version that ASOP ran previously. This is an important check because, for example, for this simp-all optimization here, due to limitations of the lean API / maybe it's also not possible to also always do this soundly, I'm not sure. The optimized version is usually correct in the sense that it behaves the same as the original version, but not always, so we need to check this. Then the second step is the most involved and does the structuring that I already talked about in the introduction. Right? So it takes this script, which is just a list of tactics, and transforms it into this tree where we focus on specific goals. And it also does this reordering where these on-goal 2 things disappear if possible. And the third part of the pipeline is global static optimization, which I will not cover in this talk because it's not so interesting. Basically, it just does some very basic rewrites on the final script. These are purely syntactic. That's why I call them static. And they work on the whole script rather than on individual tactics. That's why I call them global. Right, before we get into this, a little note about the input of the optimizer, so what we get at the start of the pipeline. We get a so-called naive script, which is a list of script steps. And a script step contains the syntax of the tactic that Aesop ran, which can also be a tactic sequence because Lean doesn't clearly distinguish between the two things. And in addition, it contains a pre-state, which is the state of Lean, if you want, before the tactic was run by Aesop, and the goal on which the tactic was run, and a post-state, which is the state after the tactic was run, and the goals that it produced. It allows us to check whether a tactic that we optimized has actually the same behavior as the tactic that we had previously, which is the entire point of local dynamic optimization, which I'll get to now. So I've already explained the issue, right? The simp all only thing is not always correct. So what do? Well, we check whether it is actually correct or not. This means that we generalize the script steps such that they can now contain multiple alternative tactic syntaxes. And we basically just try them kind of top to bottom, right? So we first try the simp all only tactic, and we check whether if this tactic is run in the pre-state of the step, it produces the expected post-state. If it does so, great, we'll take this version. If it doesn't, we'll move on to the next tactic. And the last tactic in the sequence is always assumed to be a fallback, so it's always assumed to be correct in the sense I just mentioned, so that we have some form that we can use. Now, this is conceptually very easy, but there is one technical niggle that I wanted to talk about because I think it might be of more general interest than just this work. So to decide whether a tactic produced the expected post state, we need to compare whether the expected goals and the actual goals are equal. And there is a little problem with that, which is that essentially the internal names of hypothesis and also meta variables, which I haven't mentioned yet. So what that means is, suppose we have the simp all only thing and the simp all thing. We execute both with the exact same goal, and we get two goals that look exactly the same as well. So we would certainly want to consider these two tactics as having the same behavior. However, internally, the two goals that are produced use internal names for the hypothesis, which are unique names generated by some global name generator. So the actual names that Lean uses to identify these hypotheses are unique 1, unique 2, unique 3, and so on and so forth. And hence, the two goals are not equal, kind of on the nose. And with how the Lean API is structured, I don't think there is any reasonable way that we're going to convince Lean to give us exactly the same names in both cases, particularly when the two tactics here might be implemented differently. Okay, so what do? Well, we need to compare the goals up to renaming. And I imagine that I'm not the first to come up with this, but it was not clear to me when I did this work that this was the right notion of equality, so I wanted to quickly present it here. Basically, what we want to do is we want to go through the goal, starting with the first hypothesis here, and we compare the two hypotheses. So we compare the types. Types are list alpha on both sides. So we can consider these two hypotheses the same, and we store this fact in a map down here that we are going to carry around while we compare these two goals. Then we move on to the second set of hypotheses. Again, it's list alpha, again the same. We store this identification. And now for these hypotheses here, the types are not exactly the same on both sides, but we have already remembered that we want to consider unique 1 and unique 4 to be actually the same. So we consider them the same in this case as well, and we identify unique 3 and unique 6. And we continue with the target of the goal, which I've elided here, and we do a similar thing also with meta variables, where it's slightly more complicated. So this gives us kind of the right notion of equality for comparing goals produced by different tactics with potentially different names. All right, moving on to the second and most involved stage of the pipeline, which is the structuring stage. And here, the main problem, although there are a bunch of other problems that I also discuss in the paper, but the main problem is that ASOP may solve the goals in an unnatural order. The solution obviously is, okay, we want to reorder the tactic such that they are applied in the natural depth first order, right? So we always attack the first goal first. Here's again the example from the beginning, right? We have these on-goal 2s, and we want to move these tactics to the place where they would naturally appear, right? So this one gets moved 1 down, this one gets moved 2 down, because these happen to be the places in the script where these tactics would usually be applied. Now, this is all good and not very hard, but unfortunately, it becomes difficult when we have goals with meta variables. With the problem being that reordering is actually unsound in general when goals contain shared meta variables, and I'll demonstrate with an example here. So let's say we have this tactic state. We have 2 goals. The first goal says that meta variable n is less than 42. Second goal says meta variable n equals 0. And meta variables stand for arbitrary terms to be determined later, right? So you can think of it as a typed whole in an expression. So down here is a script that works when we try to solve this goal, right? So we first run the reflexivity tactic on the second goal here. What this does is it solves the equation or proves the equation by reflexivity. In order for it to do that, this question mark n must in fact be 0. So the tactic assigns the meta variable n to 0, and therefore all occurrences of meta variable n get replaced by 0. And the first goal therefore changes to 0 less than 42. Now we run the second tactic, which is decide, which runs a decision procedure for less than on concrete natural numbers. So it's able to solve this goal, no problem. Now, if we permute these 2 tactics or reorder them, they don't work anymore, because we tried the decide tactic first on the first goal, but there is nothing to decide here. We don't yet know what the left-hand side of this inequation is. Therefore, the decide tactic will fail, and we never get to the second tactic, which would have told us what this question mark n meta variable actually is. So we lose some information, essentially, and the reordering has made a script that previously succeeded fail. How do we deal with this? I actually propose 2 methods for dealing with this. So let's take this example. This is a very synthetic example. I apologize. There are more natural examples, but I was too lazy to find them. So we have one goal here, which is true, and there exists an x such that 1 equals x and x equals 1. And okay, there is the original script down here. And we want to reorder this as much as possible. And the idea here for static reordering is very simple, right? As long as we don't have meta variables in the tactic state, we don't have a problem. We can reorder at will. As soon as we have meta variables, we stop reordering. So that's the whole idea. So we start by applying kind of the most natural tactic, right? Here there's only one goal, so we don't really have a choice anyway. We apply this and.intro. And now here there are 2 goals, but there are no meta variables inside, so we can reorder. So we take the next tactic that applies to the first goal here, which happens to be the third tactic, true.intro, in the original sequence. Okay, now again, we only have one goal, so we don't have a choice. So we apply this exists.intro, and here we have reordered, and that's fine because there was no meta variable. Okay, now we have a goal with meta variables. Now we need to become more careful, and becoming more careful basically just means, okay, we take the tactics from the original script in exactly the same order that they were applied there. So we get this and.intro, and then on the second goal we run refl, and on the first goal we run refl, and we get a partially ordered script. However, you might have noticed that in this case, if we go back to this state, it would have actually been fine to reorder the remaining 2 tactics as well, right? Because we just run refl on both goals, and it doesn't matter in which order we do that. And that's precisely the idea behind the other approach to reordering, which I call dynamic reordering. So here, the idea is when we're in the state, we try to reorder kind of optimistically, because even though reordering is unsound in general, it is sound in some cases. So we can just try it and apply this last refl tactic first. And then we happen to get a goal that is actually solved by the remaining tactic, so that's fine. Now, what if this tactic here hadn't succeeded? Well, basically then we reverse the reordering, right? So we backtrack and we try a different order, and then try the dynamic reordering algorithm again. This makes it exponential, which is a bit unfortunate. However, there is kind of a sanity check that we do after each reordering decision to make sure that, in this case, this REFL tactic has approximately the behavior that we were expecting. The precise sense of this is discussed in the paper and also has to do with this kind of equality between goals algorithm. And this sanity check should, in practice, cut down on a lot of the kind of exponential or a lot of the choice points that make this algorithm exponential. And indeed, in the paper, there is an evaluation where I try this script generation functionality on all the 6,000 ASOP calls in MATLib. So I generate scripts for all. And it turns out that the dynamic reordering is slower because it does need to re-execute some tactics, but it is still kind of within acceptable bounds. Most dynamic reordering calls are still relatively fast. All right, so to conclude the talk, I've presented a 3-step pipeline for tactic script optimization. I focused in particular on 2 of the steps, which are local dynamic optimization and structuring with these 2 reordering algorithms I discussed. If you want to know many technical details, including precise descriptions of these algorithms and a lot of stuff about specific ways that lean represents hypothesis names and so on and so forth, you can read all of that. I hope you're happy that I spared you from this kind of stuff. And of course, as future work, I think many more optimizations could be added to this and should be added to this. For example, for the AI use case, it would be very nice to detect which tactic steps are actually required for the final proof, because the AIs tend to insert a bunch of steps that don't actually contribute anything to the proof. So that's an obvious optimization that could be added. And there are a lot more. I'm sure you can probably think of some as well. All right. That's all I had for you today. I was a bit quicker than I was expecting, so that means we have a lot of time for questions, and I hope you actually have some.
Thanks, very interesting. I was wondering, you talked a little bit about why reordering is unsound, and the example you gave was with these meta variables. And I think you said that it's unsound if there's overlap between the meta variables in these goals. But then you went on to explain that, well, my impression was that you basically just try to swap these things, and if it doesn't work, then you revert back, right? But isn't there like a more subtle way where you check if there is actually overlap between these meta variables before doing that?
Yes, great question. So indeed, the current implementation considers this goal here already kind of unsafe, even though we actually have only one goal. And if we had 2 goals here where we have like a meta variable x in one goal, a meta variable y in one goal, the current implementation would also consider this unsafe, even though it is perfectly safe. The reason for that is technicalities. Basically, it's quite annoying to carry around a tactic state that accurately represents which meta variables occur in which goals, because the tactics that are executed can have an effect on the meta variables that appear in different goals, because they can assign a meta variable that appears in a different goal, and then you get basically changes in these meta variables. In order to track that precisely, one would have to do a lot of bookkeeping, which I didn't want to do because the static reordering algorithm is incomplete anyway. So I hope that this is not a big problem in practice. If it is a problem in practice, it could be fixed.
In the static reordering, most of the examples, so when you do on goal 2, it's more, then it can generate itself sub-goals. And is it easy to keep track on which goal the next tactic will refer to with respect to the original organization?
Yes.
The
so
bookkeeping stuff?
Yeah, so the goals are all identified by unique names anyway in the original naive script, which makes it relatively easy to track which goal a script step refers to. The only thing that we need to do is when doing this when executing this algorithm, we need to keep track of a representation of the tactic state so that we know at which position at which position each goal that we are currently working on is located. That is necessary to generate these on goal 2 thingies, for example, here. And yeah, this is a bit annoying. It's also connected to the previous question where we don't keep track of this tactic state precisely, but having some kind of approximation of the real tactic state suffices for this purpose.
Hi, I first have a brief suggestion. So I would add a mode where I could at least add optionally the statement that this was produced by a ASUP. Because if a proof breaks later on, then one knows, oh, I just have to remove it and run ASUP again, right? I mean, this is what we usually have in Isabel. You see a Metis line with a long list, and you know, oh, this was Sledgehammer, right? And then you run it again. My question is actually, did you make timing experiments whether these scripts really are always faster? Because what I experienced in Isabel is sometimes that you can switch between either getting a compact Metis call or getting an explicit proof script with lots of details, etc. But then parsing this whole thing, because intermediate statements are written in Isa, takes longer than running everything without parsing on the internal tactics.
Ah, interesting. So I did not do timings on this because I thought it was very, very likely the case that the produced script would almost always be faster. So my experience with the lean tactic system is that parsing the tactics is essentially free compared to the time that lean spends running the tactics, particularly when there are simplifier calls in there or something like that. These tend to take much longer than anything else that happens during tactic execution. So I would expect that it is possible that the explicit script is slower, but only in cases where all the tactics involved are so fast that we are basically talking like single millisecond range anyway. And in that case, it doesn't make a difference.
There was, I guess, a step that you, I don't know, omitted, where like even you're reordering them, but it's still reordering into another straight line script, right? So at some point, this has to turn into a tree. Like how does that work? Is that okay?
Yeah. So C paper. It's a bit hard to describe because there's actually a multi-stage computation involved. But basically, we run over the script, we simulate the tactic state again, and that gives us the tree structure of the eventual script. And then there's a separate rendering pass that takes this tree structure and outputs the right combinators. So it's a whole other process.
Is that something that you can do without having to rerun the tactics?
Yes, this is fully static.
So I'm a COC user and not a lean user, but a very common sort of pattern that I find myself using is when sort of the second and the third and the fourth subgoals are more or less trivial. but it sort of does the unification of the meta variables that I want. So it's sort of apply this tactic, and then you have semicolon and braces and say second and third and fourth subgoal, do these one-liners. And that makes, to my mind, more readable proofs, because you can sort of get away with the simple one-liners and sort of continue with what is actually sort of the core of the proof. Is this something you do in Lean as well, or would this seems like it would sort of maybe muck up deliberate structure for readability?
Yeah, so I mean, we are starting here with an initial ASOP proof, right? So at the start of it is, well, at the very start, is this thing where we run ASOP and it solves the goal fully. So in some sense, we've already done the automation, and if you want this automated thing, then you can leave it at that. I think there is a case to be made actually for partial automation, where we don't generate the fully explicit script, but maybe we just run the more expensive things explicitly, and then once we have a goal that's very easy for ASOP to solve, we could insert ASOP calls in here. So then, you know, we get kind of the interesting steps explicitly and the not so interesting steps implicitly. I think this could be a nice idea.
Okay, let's thank the speaker.
Thank you.
Our last speaker is remote, so Asta is telling us about the Isabelle framework for synthetic completeness proofs.
And others. I am Asta Helga From. I'm from the University of Copenhagen. I couldn't make it to the conference, but I am thankful to the organizers for letting me present anyway. My paper is an Isabelle Hull framework for synthetic completeness proofs. What does that mean? Well, say that we have a new and exciting logic. We have a means of deriving phi from some list of elements A. And now we want to prove this central completeness property, that if phi is valid under a set of formulas gamma, then we have some derivation of phi from gamma, where I simply mean that we are deriving phi from a list of elements A from gamma. The problem is we want the computer to help us prove it, and that's where the framework comes in. The strategy that we will be encoding is the following. Assume phi is valid under gamma but has no derivation. Then you can say that the negation of phi along with gamma is consistent. It's consistent because it doesn't allow us to derive a contradiction. And when we have such a consistent set, well, then Lindenbaum's lemma gives us a way to extend it into a maximal consistent and witnessed set. This simply means that we have probably more formulas than before, but we also have all the ones that we started with. Any formula that we don't have is not included because it would be inconsistent to do so. And the witnessed part means that whenever we have an existential formula, then we also have a witness for it. Whatever existential means, we will be discussing this. Now, when we have such a maximal consistent set, we can prove a truth lemma, which says that any formula in the set is exactly in the set when the set models that formula. And now, since we have both the negation of phi and we have all of gamma in our set, that set models those formulas, but that contradicts the initial assumption that phi is valid under gamma. And so by contradiction, we must have this derivation of phi from gamma. Now, when we do this in Isabelle, what do we want? Well, we would like to prove Lindenbaum's lemma exactly once. We want to prove it in the abstract. So I'm going to assume a notion of consistency that is not concrete, but just has these three properties. We want that subsets preserve consistency. We want compactness, that inconsistencies are finite. And then we want that whatever witnesses the user adds, they preserve consistency as well. to help prove the truth lemma, we would like to know that we can sort of reflect the proof rules into our maximal consistent sets. So say we have a proof rule where we can always derive some top element, then that top element should also be in our sets, right? Finally, we would like to help guide the process of proving the truth lemma by splitting it into syntactic and semantic parts. So we will be introducing this notion of saturation, and prove that MCSs are saturated, which for instance for the existential operator means something like whenever we have an existentially quantified formula in our set, it's because there exists a parameter such that we have an instance with that parameter in our set as well, and vice versa. Saturated sets are going to be models, and then when you combine this, you get that MCSs are models. But the fact that saturated sets are models will be proved entirely by Isabelle-Hall automation, so we've sort of factored out the part that Isabelle can deal with easily. How do you do Lindblom-Davos lemma in Isabelle? Well, I started from this transfinite proof by Chang and Keisler in their model theory book. I have generalized it from first order logic. I also work in higher order logic instead of set theory, so we cannot just have a function from ordinals to enumerate our formulas, but we will see how to deal with that. I've also chosen not to expand the language, which is now a type, so whatever language the user comes with, I work with that by instead assuming that I have enough parameters available. The formalization is inspired by earlier work by Stefan Berghofer, but his proof is not, does not support uncountable languages. So now say we have an abstract consistency predicate on formulas. The user comes, they say, hey, to me consistency of a set of formulas means this. Then I ask them to prove two things, that subsets of consistent sets are consistent, and that inconsistent sets have an inconsistent finite subset. If they also want to witness some of their formulas, I ask them to give me a witness formula that builds instances of existential formulas, and I ask them to tell me what parameters mean for their syntax. Then I need that if you take the parameters of a formula, this set is finite. If you take the parameters of all your witnesses of a given formula, then this set is finite. And I need that given that you have infinitely many parameters available to choose from, you're going to build me some witnesses that preserve consistency. This so far is enough to give some definitions. It's enough to say that a set is maximal exactly when all formulas that are consistent with it are already included in it. It's enough to say that a set is witnessed when every included formula has witnesses included. We are sort of forgetting the sets of parameters from which these witnesses were built. That's just existentially quantified, but it doesn't matter because we have the witnesses themselves. And now we can have a convenient abbreviation, MCS, that just says that a set is consistent, maximal, and witnessed. Now, the way you actually take a consistent set and extend it into a maximal consistent set is to do it one by one. To do it one by one, we need a way of enumerating formulas. And the easiest way in Isabelle is to assume an infinite cardinal order, and then we can use well-ordered recursion on this infinite cardinal order, and in that way we can get through all the formulas. This gives us three cases. It gives us a case for zero elements, a case for successor elements, and a case for limit elements. But the overall idea is simply that we add formulas and their witnesses exactly when consistency is preserved. So you can see the three definitions down here. And the first definition, we invoke this well-ordered recursion with three cases. In the base case, we just have the set we start from, S. In the successor case, we have the successor definition, and in the limit case we have the limit definition. And if you look at the successor definition, it states very simply, if it's consistent to add our formula, then we add it along with its witnesses, and if not, then we just forget about it and we take what we already have and use that. In the limit case, we add every subset that is strictly smaller, built from a strictly small element. Now, if you take the union of all of these sets, so you take a initial set and you extend it for each formula, which is also now a sort of a number, you take the union of all of these, then that is your maximal consistent set. Of course, you have to prove this. The proofs in my artifact follow from Chang and Keisler's book. Again, we have this idea that inconsistencies are finite, so that helps us a lot when proving consistency. And then I have introduced the assumption that we always have at least as many unused parameters as we have formulas. So in that way, whenever we encounter a formula we need to witness, well, then we have unused parameters to do so. And we can prove that this set is an MCS. Now you may be thinking, what if I have a logic where I don't need the witnessing stuff, I don't need the parameter stuff? Well, Isabelle has this nice feature called a sublocale, where I can go in and I can specify up front for you that this set of witnesses is empty and the set of parameters is empty, and then you don't need to worry about the assumptions that deal with those. So what does this actually look like for something like a concrete proof system? Say you have a natural deduction system for first order logic, so here it's specified as an inductive predicate. And if we say that consistency means that this falsity, which is in our syntax, is underivable, no matter what list of elements we take from a set, we cannot derive falsity from it. And if we say that witnesses of existentials are just instances where we pick the parameter so that it's unused using Hilbert's choice operator, then building an MCS using the framework amounts to proving these 6 goals that the framework spits out. If you look at these, most of them are very trivial. From the way we define consistency, the consistency properties hold, the 2 first hold very simply. Finiteness also holds very simply from just the finiteness of our syntax. Only number 5, that these witnesses that we add don't destroy consistency, actually requires a little bit of proof. The last goal is simply that we have an infinite number of formulas, such that we can have this infinite cardinal order on them. So now that we have our MCSs, what can we say about them? Well, so far I have deliberately kept the proof system abstract. I've only assumed a notion of consistency, but let us make some assumptions. So say we have a notion of deriving a formula from a list of formulas, that we can derive assumptions, and that we can rearrange and contract and weaken our assumptions. Say furthermore that consistency means that something is underivable. So it's not the case that we can prove everything. In a consistent set, there's something we cannot derive. This is actually enough to tell us that a formula is excluded from an MCS exactly when including it would be explosive. So including it would lead us to be able to derive everything. The proof is fairly simple. So from left to right, let's say that it's not in there. Maximality tells us that including it would be inconsistent, and therefore assuming it would be inconsistent and would be explosive. Let's say that from right to left that having a P in there is explosive. Well, then including it is inconsistent and contradicts our assumption of consistency. To talk about when a formula is included in a maximal consistent set, we also need a general cut principle. So say we can derive P from A, from P and B we can derive Q, then we can cut out the P and derive Q directly from A and B. Now, if P is in our set, we can just derive it as an assumption. Let's say we can derive A, then we would be able to prove that, let's say we can derive P, then let the inclusion of P would follow by maximality if we can prove that P is consistent with S. So, looking for a contradiction, assume that it's not consistent, that it's actually explosive, but then cut gives us that two lists of elements from S themselves are explosive, and this is a contradiction. Now, these were two sort of abstract lemmas. What if we have maybe not a whole proof system, but what if we have a concrete piece of syntax, a concrete proof rule? Can we actually use it to say something about that? So let's say we have a piece of syntax for a falsity element, and we have the proof rule that says if we can prove falsity, then we can prove anything else. Then we can mirror this, and we can sort of move from proof system to MCS, and we can say, well, if this falsity element is in our MCS, then anything else is also in there. What you do is you assume the falsity element is in there. The presence lemma gives you a derivation of falsity. Now you're in the land of the proof system, so the elimination rule gives you a derivation of your formula P. And then you go back to the MCS world, again using the presence lemma, and you get that from the derivation that the P is in your MCS. You can also have a more complicated operator. You can have negation with both an introduction and an elimination rule. And here it's easy to prove that P is in S, if and only if the negated P is not in S. The proof rule is very similar to before, but here you also need the absence lemma when you do the introduction rule. We can go even higher. We can not just have basic operators, we can actually have quantifiers. So say you have some abstract notion of what it means to existentially quantify a formula, and you have a notion of instantiating it with a concrete parameter. If you then have a correlation between this piece of syntax and your witnessing function, and you also have an introduction rule, then you can lift it to get the property that we have already looked at, which says that if an existential formula is in your MCS, well then that's exactly because you have an instance in your MCS. And here from left to right you just use the Lindenbaum construction, which adds these along the way. And from right to left you use the presence lemma and the introduction rule. So as I said, you can sort of move between proof system and MCS. The framework provides some existing results for disjunction and conjunction and the usual operators, but you can also prove your own, and we will see an example of this. Actually, the already provided examples are flexible enough for something like the hybrid logic global modality. The global modality says that a formula holds at a world when that exactly when that formula holds at all worlds. And if we now imagine that we have a calculus that labels formulas with what are called nominals that sort of name the worlds, then we can just treat the global modality as a universal quantifier. So when you form the modality, you don't change the world. You're in world I, you stay in world I. But then when you instantiate the modality, you switch to the world that you are instantiating it with. And if you supply this to the framework and you prove that you have the proof rules to support this, then reflection would give you exactly the property that you expect, which is that when you have a global modality at a world I in your set, well, that's exactly because you have the formula under the modality at all worlds in your set. Now we get to the final part, the truth lemma. How do we deal with that in a nice way in this abstract computer setting? Well, we need a syntax independent handle on subformulas. So we need a way to sort of talk about truth lemma without talking about the concrete syntax. So what you do as a user is that you take your semantics. For instance, you might have that a conjunction holds exactly when the conjunct holds. Then you abstract away the recursion, and then you allow me as the framework provider to plug in my own relation. So instead of hard coding this models relation, I can plug in my own relation. But what's going to happen is that this relation is applied to the subformulas in a way that respects the semantics. It's congruent with the semantics. If we now take a relation that is parameterized by our MCS, so instead of saying our model models the formula, we're saying that the formula is in our MCS. Then we can take the truth lemma clause for conjunction and we can write it abstractly. So for conjunction to be in our set S, we need both conjuncts in the set. If we just write this set inclusion using our relation on both sides, then it looks very long. But then when you look on the right-hand side, you can see that that's exactly what the generalized semantics would give you if you plug in our own relation. And now now on the very last line, we haven't split up the conjunction. We have just used this relation and this generalized semantics, and we, by unfolding definitions, we actually get to the clause that we want. So in general, we can state saturation with the equation on the bottom, which says that a formula is related via M to S exactly when the subformulas are, in a way that respects the semantics. I didn't use the model. Why did I do that? Well, actually, I should do that. In general, it's too naive to ignore the model and just say the formula is in the set. For first order logic, for instance, we need to account for quantifiers. So when you go under a quantifier, what happens to the formula? It's going to have an unbound variable, but information about that unbound variable is stored in the model. So we should sort of apply that model as a substitution before we look it up in the set. And that's what gives you that when you look at the universal quantifier, you're actually looking at instances of the formula instead of just the formula with an unbound variable. In hybrid logic, we saw that we can label formulas with the worlds that they are true at. In the same way, the model here is going to know what the current world is, and we should label the formula with the current world before we look it up in the MCS. And that's what's going to give you that when you look at the diamond modality, you are actually going to change worlds instead of just staying at the same world. Can we do this in the abstract? Yes, we can. We only need a couple of definitions, and we need, for instance, to know that the semantics with a hole in it is faithful to the semantics without a hole in it. So if M models P, well then using the models relation, the generalized semantics should still hold. And now we can write down the equation that I had before with a slight generalization that we can allow for multiple models per MCS. So instead of saying that an MCS only gives rise to one canonical model, then we can allow for it to give rise to multiple. What can we do when we have this notion of saturation? We can say two things. We can carve the truth lemma in two. So we can say that saturated sets model their members and that MCSs are saturated. This very easily combines to say that MCSs model their members. But now that we have introduced this distinction, we can have Isabelle Hull generate complete proof applications. This factors out the semantic part that the automation can take care of. And then it leaves us with the semantic part that relates very closely to the reflection. So for instance, for first order logic, saturation is going to ask of you exactly what reflection gives to you. For the global modality in hybrid logic, it's not quite as simple because here we're going to have some equivalence classes. But still, reflection gets you very close, and the proof search of Sledgehammer gets you all the way there. So we have sort of reduced the problem to something where the automation can take over. For the satisfaction operator, I did not give you any notion of what reflection gives you. But I did give you these basic building blocks of the absence and presence lemmas, and then if you have suitable proof rules in your calculus, Sledgehammer will be able to find the thing that you need. In summary, the framework helps you build maximal consistent sets. It helps you reflect the proof system into these maximal consistent sets, so you actually know something about their structure. And it helps you carve up the truth lemma in a way that makes the proof assistant more useful. The artifact includes strong completeness for sequence calculus and Tableau in the propositional setting, for a modal logic Hilbert system, and for natural deduction systems for first order logic and hybrid logic. And I'm excited to see if anyone else wants to apply it to something more complicated. The limitations are this need for compactness, which is prevalent in the proofs. And if you want to go beyond just building your MCSs and actually use this reflection part of the framework, you need to have this general cut principle. Blanchette, Popescu, and Reitel have mechanized another framework for completeness proofs. There's this analytic, so they use abstract derivation trees instead of MCSs. This is a more operational perspective, which has its disadvantages and advantages. One of them is that you can use it very directly to generate a prover. There's work in category theory, which has come to some of these same abstractions to me, which I found very interesting. There's also an assumption of compactness and cut. And then finally, I am working on using Melvin Fitting's consistency properties instead of this abstract notion of consistency that I have. Here you sort of specify the reflected proof rules up front, and that allows you to get more info about your MCSs without needing, without having to prove the general cut principle. My idea is to use Mullian's uniform notation to do it in the abstract. Berghofer has sort of done it for concrete first order logic syntax. And it works very well for strong hybrid logic, so I think it will work for other things too. Here's an abridged bibliography. The Isabelle code is available on Zenodo. It's also in the archive of formal proofs if you go to the development version. Thank you for listening. Hello, ladies and gentlemen and others. I am Esther Helga From.
So I guess we have Esther on Discord now, so we can probably ask questions. Anyone has questions? Oh, can you hear us?
Yes, I can hear you.
Does anyone have any questions? I guess, I mean, I could ask, you talked a lot about proving consistency. Does any of this help for proving soundness as well? Or would you use different methods?
No, the analytic framework that I listed as related work has some help for proving soundness in this more operational setting. It's not part of my framework.
Do you think that this is like a fundamental restriction of the thing, or is it just that you hadn't got to that, or like?
I heard two questions at once.
Well, I was asking, is this something which is a fundamental restriction of the technique, or is this something that you hadn't gotten to?
Well, in my world, soundness is one lemma of the paper, and then completeness is 15. So it's simply a matter of focus. I'm sorry, I'm hearing myself very delayed. Oh, I'm sorry. This is my own fault. What was the other question? Sorry.
I have another question, but it's probably different from the one you had before. So forgive me if I missed this in your talk, but your framework is meant to cover this pattern in the proof that we see for completeness in many different logics. Do you like how many instantiations of this do you have currently? I think I've seen this in my limited experience. I've seen this pattern of proof for completeness being used for modal logics, for instance. So which modal logics can you cover right now?
So concretely, I have system K, and I see no reason why I couldn't cover any normal modal logic.
I see. So that would be a matter of just more labor, right?
Yep.
Okay, thank you.
In your construction, you did this recursion over successor zero and limit induction, where you needed this ordering. Do you already know or always know that such an ordering exists on the set of formulas, or does your formula type have to enforce certain constraints?
No, we are in Isabelle Hall, so we have the axiom of choice, and we can just impose this ordering. So it's not an extra proof application for the user.
Okay, if there are no more questions, then let's thank the speakers. And we have a coffee break now. We're coming back in 30 minutes.
This session, the business meeting will take place. So we hope that many of you will stick around for that to have a discussion afterwards. But otherwise, let's get started. The first talk will be on differential privacy, and Tetsuya Sato will give the talk. Please.
Okay, thank you for introduction. So I'd like to talk about formalization of differential privacy in Isabelle Hall. Okay. So in this talk, I first explain what is differential privacy and its intuition and definition and the results that we formalized. Next, we explain the formalization of differential privacy in Isabelle Hall. So we explain the formal definition and formalization of basic properties of differential privacy. Then we formalize the Laplace mechanism. Finally, we will see the formalization of report noisy max mechanism. Okay, let's move on to the introduction of differential privacy. We first consider a scenario of privacy leakage. Imagine an apartment. 999 people live here, and the apartment has the average income query. And then step one, the average income is $5,000. So in the first step. Step two, now Bill, the 1,000th person joined the apartment. Then the average income changes to $5,000 plus one. Step three, then in this case, the average income query shows only just the average of income. However, it leaks the Bill's private income. We can calculate $6,000. So it is a very cheap scenario of privacy leakage. I want to say that the average income does not show the Bill's income itself, but using the background knowledge, so privacy can be leaked. To prevent such privacy leakage, we can add noise to the query of average income. So in such noisy query, for example, the average shows as follows. In the case of 999 people, the query shows $5,000 plus 2. Here, the noise is plus 2. And in the case of 1,000 people, the last person is Bill. The average shows $5,000 plus 1. Here, the noise is plus minus 0. So importantly, the amount of noise is basically small. However, it is statistically harder to determine the Bill's income. So it is an intuition of differential privacy. Actually, to realize the differential privacy, we need to discuss the specification of the average income query, and we need to discuss the shape of noise. Okay, let's move on to the definition of differential privacy. So in the definition of differential privacy, we consider a randomized query. A randomized query M from X to Y. Here, X is the domain of data set. Y is the domain of output. The randomized mechanism M is epsilon delta differentially private for any adjacent data sets, D and D prime. Here, the adjacency means that the two data sets, D and D prime, differs only in one record. So for adjacent data set, D and D prime, the distributions MD and MD prime of output of the mechanism M satisfy this inequality condition. So this condition seems rather complicated, but the intuition is very simple. The ratio of probability between MD and MD prime is bounded by e to the epsilon, except in the probability delta. So in short, the parameter epsilon stands for the ratio of probability between MD and MD prime, and delta is the probability of error. Importantly, if epsilon and delta are small, the two distributions, MD and MD prime, are hard to distinguish. In particular, if both epsilon and delta are 0, the distributions MD and MD prime are the same. So I here remark on the adjacency of data set. Differential privacy is a definition to hide the small change of data sets. So it depends on the structure and the adjacency of data sets. In this talk and in my paper, we consider data sets and adjacency as follows. First, each data set D is a finite list of natural numbers with length n. Here, each record D of I shows the number of data in class I, and the data set D itself can be understood as a histogram. Next, the adjacency of data set is defined by the L1 metric. D and D prime are adjacent if and only if L1 metric between D and D prime is bounded by 1. In this case, D and D prime differs only in one record. Okay. Next, to realize differential privacy, we need to add noise, I said. So here is a typical mechanism of noise addition of Laplace mechanism. Sorry. It is a typical mechanism of noise addition. So a noise adding mechanism of Laplace distribution. So lap B is a, so for given scale parameter B, we can consider the noise adding mechanism lap B. And then for given value x, lap Bx is a Laplace distribution of mean x with scale B. So definition of Laplace, okay. So here is density function and the shape of Laplace distributions. And the Laplace distribution has a nice property for differential privacy. So if the given values x and y differs only, difference between x and y is bounded by R, then the ratio between the Laplace of x and Laplace of y is bounded by e to the R over B. So in short, these two distributions, the ratio of two distributions are bounded by some constant everywhere. Okay, next, Laplace mechanism, it is a typical mechanism for differential privacy. So it is a mechanism adding Laplace noise to each element of output of the process F. Here, we consider a process to anonymize F. F accepts the data set and returns the M values, tuple of M values. And the Laplace mechanism adds noise to each x of I, and then produce the noisy tuple. So we can discuss the differential privacy of Laplace mechanism. We use the sensitivity of the process F. Sensitivity is defined by the least upper bound of the difference between FD1 and FD2, where D1 and D2 are adjacent data sets. So using this adjacency, the differential privacy of Laplace mechanism is delta F over B, 0, differentially private. So it is a typical example of differential privacy. Here, report-noisy max mechanism is an application of Laplace mechanism, but so it contains a non-trivial result. Okay, first, report-noisy max returns the index of maximum value in a Laplace mechanism for the counting query. So first, we consider a Laplace mechanism for the counting query. So counting query means that each counting query counts the number of data of some classes in a data set D. And then each counting query has a sensitivity 1. And then, so then we consider a tuple of M counting queries, and then this part has sensitivity M. So we also consider the scale parameter 1 over epsilon. So, and then we apply the argmax operation after that. So naively, the differential privacy of report-noisy max mechanism can be evaluated as a M epsilon 0 differentially private. However, it is actually epsilon 0 differentially private regardless of M, the number of counting queries. The proof is not so simple. It is done by evaluating the distribution of report-noisy max mechanism directly, and by applying the specific properties of argmax operations and counting queries. Okay. So we briefly see the result what we formalized. In this work, we formalize differential privacy. We give a differential privacy library in the continuous setting and in a peripheral assistant Isabelle Hall. So the motivation to the continuous model is as follows. First, a continuous model is more general than the discrete model. Second, some studies of differential privacy consider ideal mechanisms written in the continuous setting. So for example, in the study of floating point implementation of Laplace mechanism by Mironov, so in the paper, so snapping mechanism, which is a floating point version of Laplace mechanism. So in the proof of its differential privacy, we need ideal version of Laplace mechanism. Secondly, so in the study of F differential privacy, which is a very latest extension of differential privacy, so to prove the composability of this, we need a continuous model, even if we consider only the discrete mechanisms. Okay, I remark that formal verification of differential privacy in the discrete setting is already implemented in several proof assistants. In Coq, for example, in Coq, the certproof library contains a discrete version of differential privacy and the implementation of relational forward logic reasoning about differential privacy, and the discrete version of Gaussian mechanism. In Dean, so in the SAMPSAT, it is a very recent formalization of differential privacy. So in the SAMPSAT library, there is a discrete version of differential privacy and a discrete version of Levy differential privacy. It is a relaxation of differential privacy. And also it contains a discrete Laplace and discrete Gaussian mechanism. And interestingly, it also contains a causal generation. So coordination to the executable code. Then, in this work, we formalize differential privacy in the continuous setting. I focus on the continuous setting and in a proof assistant Isabelle Hall. Our formalization consists of the 3 parts. First is the mathematical foundations. So there are many preliminary theorems, and so measurable space is a finite list, and the Laplace distribution itself. And the second part consists of the main library for differential privacy. So we implemented the statistical divergence for differential privacy, and formalization of differential privacy and the basic properties of differential privacy. And then we formalize the Laplace mechanism. The last part consists of the formalization of report noisy max mechanism. Okay, so in our formalization, we use probability theory library in Isabelle Hall. It is a standard library of Isabelle Hall. So the standard library contains the measure type and the monad for probability, which is called as a Gilly monad, and Radon-Nikodym derivative, which is used for the composition theorem of differential privacy, and the Lebesgue measure. So in our formalization, we use various constructions in the standard library, in particular a probability theory library. Okay. Then we finally check the Isabelle Hall formalization of differential privacy. So we recall the we recall the definition of differential privacy. A randomized mechanism M is epsilon delta differentially private if for any adjacent data sets and D and D prime, then the distribution MD and MD prime satisfy this condition. So to formalize this definition, we formalize this condition first. And then we formalize this definition as this definition. We here remark that in our formalization, we consider abstract data set and adjacency. So usually, adjacency relation is assumed to be the symmetric, but in our formalization, the symmetry is dropped. Because in the proof of report noisy max mechanism, we use asymmetric adjacency relation in the proof. So in our formal definition of differential privacy, we have two inequality conditions in both sides. Okay. Then we formalize the several basic properties of differential privacy. First, differential privacy is stable for post-processing. Consider a mechanism M. It is epsilon delta differentially private. Then, for any post-process F, the composition of the private mechanism F to the private mechanism M and the post-process F is still epsilon delta differentially private. So here is our formalization of stability for post-processing. And actually, we provide the formal proof in Isabelle Hall. So it is very simple. Second, differential privacy also has the composition theorem. It is a main feature of differential privacy. So intuitively, we compose the private mechanism M and N, epsilon 1 delta 1 differentially private and epsilon 2 delta 2 differentially private. We compose M and N, we obtain the epsilon 1, epsilon 2, delta 1, delta 2 differentially private mechanism. So here, M accepts only the data set. However, N accepts the data set and accepts the output of M. So to describe this condition, we need to assume that for any Y, which is output of M, so it satisfies differentially private with respect to the parameter x. So in the similarly, we provide the Isabelle Hall proposition and we give the formal proof. And then we formalize Laplace distribution and the Laplace noise. And we first Laplace distribution. So the formalization is inspired from the formalization of normal distribution in the standard library. So, and we consider the density function and the cumulative distribution function, and we prove these correctness, and then we formalize the Laplace noise mechanism, formalization of Laplace noise. So it is a Laplace distribution centered at a given value x. And then we formalize, we prove that so this construction satisfies the desired property. Next, we consider the tableau of Laplace noise, bundles of M Laplace noise. So in the formalization of this construction, we use list instead of tuple for simplicity of formalization. Here, the construction wrap this list, add noise to the each entry in the list of real numbers, and then returns the noisy list. So we define this construction recursively, and then we show the correspondence to the desired definition. Then we formalize Laplace mechanism. Okay. So to give the Laplace mechanism, we need to define the sensitivity of the F to anonymize. And then the definition is so rather straightforward with respect to the its mathematical definition. And then we define the Laplace mechanism using the previous construction of Laplace noise. And then we prove the differential privacy. So in the proof, we use the composition theorem of differential privacy and the nice property of the Laplace noise for the differential privacy. So we here remark the formalization of data sets. So we first we use list instead of tuples, and so to define the adjacency of data set, we introduce the L1 metric between the list. So in the construction of such metric, we use the local metric space in the standard library of Isabelle Hall. Then we finally formalize the report noisy max mechanism. The formal definition is rather simple. So we formalize this part and the counting query, and so first, and then we put the construction of Laplace mechanism. So then we show the differential privacy of the report noisy max mechanism. So in the paper, we provide the naive evaluation of differential privacy and the final evaluation of differential privacy. So the proof of the final evaluation is very complex. For detail, see the proceedings. Okay, we conclude my talk. So in this work, we develop Isabelle Hall library for differential privacy in the continuous setting in Isabelle Hall. So in this talk, we omit almost all the detail. For the detail, check the paper. And so we we have formalized the differential privacy of the report noisy max in the continuous setting and related to basic results. And here is my future work. So ultimately, I'd like to formalize the stochastic gradient descent mechanism for differential privacy. So in the construction of gradient, for the differential privacy of this mechanism, we need to formalize the relaxations of differential privacy, in particular Renyi differential privacy. For the technical basis of the Renyi differential privacy, we want to formalize the F divergence. Also, so I also want more examples that based on the continuous model, for example, continuous version of exponential mechanism. Thank you for your attention.
Thank you very much. All right, we have some time for some questions. Anyone?
So thanks for the talk. You mentioned that one of these proofs were complex. Is this complexity due to the complexity in the paper proof, or is just the automation in Isabelle not working well with dealing with probabilities, etc.?
It is a kind of complexity of paper proof. So, so a student is proving the report noisy max in the discrete setting. Even in the discrete setting, the proof costs over the 1,000 lines.
Thank you.
So, and my proof in the continuous setting costs about 1,500 lines. So, we need to convert the program of the report noisy max to evaluate the report distribution of the report noisy max so correctly.
Thanks. Then there's another question here.
Thanks for the talk. Have you considered building some kind of program logic on top of this definition of differential privacy?
Sorry, I couldn't get, keep your voice up.
Yes. Have you considered building a program logic on top of this in the style of APRHL or?
APRHL?
Yes.
So, sorry, please repeat the question. Sorry.
Have you considered, or would it be possible to build and formalize
okay, it is possible.
program
Okay,
logic?
I see. Actually, our proof contains central data. So divergence for DP is a central data of the program logic for the quantitative difference of computational effect. And so APRHL is generated from this data and several results on the specific result. So I believe that we can implement the APRHL, but I choose the direct one. So, but I already have the central data, and if we want, we use from this, and we can give the relation lifting, and then we formalize the APRHL.
Thank you very much. Other questions?
Do you think your proof can be formalized in ROC or Lean as well?
Huh?
Do you think your proof can be formalized, the continuous part, in ROC, like following the work of Bart and other?
Sorry.
Do you think your proof can be formalized in ROC or Lean as well?
Lean. Yes, I think so. I think so. I think so. So I think so. Yeah. I think both Lee and Koch already contains the technical background of our formalization. So in theory, in Koch and Lee, we can formalize the so we can formalize as our paper, and but I choose Isabelle Hall because so Isabelle Hall contains so many useful but subtle results on the probability theory, and also Isabel contains a powerful tool of sledgehammer. So I use so frequently of the I use the sledgehammer so frequently. So yeah. But we can formalize. Yeah. So I believe that they can be translated to the dean. Yeah, I think.
All right. Thank you very much. I think we should thank the speaker again. Yes, so the next talk will be given by Vadim Saliva, who will tell us about the Cherry C memory model. Please.
Hello, my name is Vadim Saliva. I will be talking about my joint work with my collaborators on Cherry C memory model for verifying temporal safety. So this is how this work was funded. So the goal of this work was to define a memory model for Cherry C, which is a critical component for understanding Cherry C semantics and providing framework for reasoning about security properties. Our memory model has three key components, distinguishing components. First is Cherry-specific pointer provenance tracking scheme, PNVI Cherry, a revocation mechanism to ensure temporal safety, and finally the formal proof of temporal safety of the proposed memory model. Quite a few words here: pointer provenance, memory safety, Cherry. Some of you might be familiar with them, but to bring everybody up to speed, let's start with some background. First, what is Cherry? Memory safety bugs are the major source of security vulnerabilities. And Cherry was one of the answers to that. It is a capability-based hardware architecture extending conventional ISAs to enable fine-grained memory protection. It was developed by University of Cambridge and SRI. And most notable hardware implementation is ARM Morella chip, which is based on ARM64 design and is currently available as an evaluation board from ARM. It is a mature platform with more than 30 million lines of code ported to it, which includes FreeBSD, kernel on user space, Qt, KDE, Postgres, NGIX, WebKit, and many more. There are several studies which analyzes the impact of Cherry on the security, and they show significant reduction of the number of vulnerabilities. So 30 to 70% for Microsoft Security Response Center, 56% of FreeBSD kernel vulnerabilities over past 22 years, and 73% in the open source desktop stack, which is Qt-based, KDE-based. Presently, Cherry C and C++ are the most mature high-level languages for writing code targeting hardware. Cherry C is a dialect of C programming languages developed as a C-lang LLVM C compiler fork. It is originally defined by Cherry C++ programming guide, and there is proposed formal semantic in COG and in English prose. There are two other Cherry C compilers exist. One is GCC, and second is Chariot LLVM. Across these three compilers, the three supported architectures are ARM Morella, Cherry RISC-V, and Chariot. Chariot is from Microsoft. It's also RISC-V based, targeting mostly mobile embedded devices. So the idea of the Cherry C is we represent the pointers as a capabilities. On the left side, you see the traditional pointers, how you might see them on the existing architecture, for example, 64-bit architecture like ARM64. The pointers are just 64-bit virtual address in memory. So they implemented as an integers. They could be created from integers, cast back from integers to the, you can cast between pointers and integers, and you can manipulate them for the integer arithmetic. They lack any integrity protection, and they do not prevent inappropriate use. On the right side, you see the pointer in Cherry C. It's a capability. And capability in Cherry is 129 bits. It's 64-bit virtual address as before. with some additional meta information, some additional fields. Most important ones are bounds, which control what part of the memory you can access through this pointer. And the second important field is permissions, which governs what kind of access you allowed. Is it read, write, or execution? And additionally, there's validity tag, which guards the integrity protection. And you couldn't just fake the capability. You couldn't just modify it arbitrarily. You have to derive them in a special way, preserving some certain security properties. And all of that is enforced by the hardware, and it's reasonably efficient. Next concept to introduce is a pointer provenance. And you might think that compilers think about pointers as integers, but this is not true, even not for Cherry. Consider the following example. If variable x and y in line 1 allocated in adjacent memory regions, the pointer p and q will have exactly the same bit representation. They have exactly the same value. However, depending on the compiler's decision of whether p and q could alias, the optimization could lead to the different observable behaviors as shown above. So GCC optimizer decides that they do not alias, and the initial value of y equals 2 can be propagated to the final printf, and that's what it prints. C-lang, on the other hand, more conservatively chooses not to propagate the value. So morally, the pointer p points to the, initially derived from the pointers to the object x, and point 1 pass object x. That's how we can think about it informally. And pointer q points to the first byte of the next object pointer y. So this is a notion. This is this notion. So that's exactly what this pointer provenance is. It allows you to allow the C abstract machine to track the region of the pointer, and this information can be used to justify the soundness of compiler optimization that based on alias analysis. There have been several proposals for the pointer provenance. The more mature ones is called PNVA AEDI, which is now submitted as a draft of ISO technical specification. So hopefully it will make it into the standard eventually. PNVA AEDI means pointer not via integer address exposure user disambiguation. I would not cheaper all that. You can read the standard if you proposed specification if you're interested further. Previously proposed Cherry C semantics uses PNVA AEDI scheme. And if you apply that to example before, it will tell you that the P is a pointer derived from the address of object X. And now it's pointing one past of the footprint of this object. So dereferencing this pointer, using it is indeed undefined behavior. So PNVA AEDI clarify these questions for disambiguate this situation. But Cherry hardware bounds will also prevent this right. And there is apparently there is an overlap between PNVA AEDI and Cherry. More about that later. Next concept is a temporal safety. So temporal safety ensures that objects in memory are accessed only within their intended lifetimes. In particular, two undesirable scenarios are usually considered. Use after free is an object was freed, but the memory is accessed before the underlying address space had been reused. And use after reallocation is when the object was also freed, but the memory is accessed after the underlying address space had been reused. So the difference is between the first case, you have a dangling pointer pointing to some free memory, a stale pointer, and in the second case, it can end up pointing to some live object allocated in the same space. So security implications are different between these two scenarios. However, from point of view of ISO-C, all instances of use after free and use after reallocate refer to an object outside of lifetime and is undefined behavior according to the standard. However, in the presence of undefined behaviors, compilers may generate the code which attempts such illegal accesses. Unfortunately, default Cherry protections only ensure spatial safety and will not prevent this. To mitigate temporal safety violations, the revocation mechanism is used. Revocation works by invalidating stale pointers to deallocated memory. In Cherry, pointers could be revoked by just clearing the tag bit, so it's a relatively easy, lightweight operation. But if you think about it, if you have to, each time you deallocate the object, you have to swipe all the memory, find all the pointers, and invalidate it. So it's from performance of view, there will be a penalty. Even though there are some hardware mechanisms to speed this up slightly, but usually it's staged and the sweeping revocation is used. And sweeping revocation quarantines the freed memory, and then periodically sweeps and revoke the pointers to it. So in this scheme, each allocation could be in one of three states. It could be a live allocation, which has just been allocated, and it's currently in use by the program. It could be a quarantine. It's an intermediate state that the memory is still retained, and you still have a pointer pointing to it, which haven't been revoked yet. But because it's in the quarantine, this memory space will not be yet reused by reallocators, so no new objects can appear there. There are several attempts to address heap temporal safety for Cherry in C and C++. Cherry Evoke, cornucopia, and cornucopia reloaded, to name a few, and all of them using various sweeping revocation implementations. If you look at the memory as a whole in presence revocation, it could be in one of the two states. In the clean states, the quarantine is empty, and there is no pointers pointing to non-live memory. In the dirty state, some memory is in quarantine, so there might be still dangling pointers pointing to the quarantine memory. So we start in the clean state. Each time you deallocate the object you call free functions in C, it's traversed to the dirty state, and it stays there until the revocation pass run. And then the revocation pass run, it revokes all the pointers, cleans the quarantine, and it returns back to the clean state. So now I think we have sufficient background again to revisit our contributions, what we've done here. So we examined the relation between the pointer provenance and Cherry and proposed streamlined Cherry-specific pointer provenance tracking scheme, PNVI Cherry. We defined in COG a specialized object memory model tailored for Cherry C. This model uses PNVI Cherry and includes support for generalized version of 5 existing Cherry capability revocation mechanisms. We integrated our model into existing executable Cherry C semantics and tested it against existing Cherry C semantics test suite. And finally, we formally defined and proven in COG temporal security guarantees provided by this memory model. So memory model offers an interface to dynamic memory allocation, release, and standard library function like memCPU, memCMP. Also, it offers interface to memory operations, reading and writing, and pointer actions, arithmetic, pointer comparison, alignment, and conversion. Our memory model is integrated into Cerberus. Cerberus is executable ISO C11 semantics, originally developed by Kevin Memarian at Cambridge. It is a concrete memory model, which means it uses integer addressable memory space, and it also keeps tracks of whether memory at given address was initialized, so it deals with initialized memory as well. Originally, the implementation was forked from the Cerberus C11 concrete memory model, which used PNVA AUDI, but the original model was written on a camel because we wanted to prove things about that. We rewrote it in COG. We also replaced PNVA AUDI with PNVI Cherry, and we added support for revocation. So that's how it's significantly different from the previous one. Speaking about memory model, it will be useful to contrast it to the memory model of ComCert compiler many of you are probably familiar with. So in the ComCert compiler, the pointers are pairs. It's simplified, obviously. It's tuples pairs of a block ID and offset within this block. Within the ComCert semantics, each object is allocated as a distinct block. And whatever pointer arithmetic you can do, you can just change the offset within this block. It could never span and could never jump to the next object. So this is a very convenient scheme from semantics point of view because you have this explicit relationship between the pointers and memory allocations, which are one-to-one to objects. This is what we called provenance before. So this is explicitly available in the ComCert. But this memory model of ComCert makes some things more difficult. For example, it's more difficult to express and reason about pointer arithmetics, or for example, pointer bit manipulation and pointer to integer cast. Although there's some research extending it for that capabilities. In Cherry C, the pointer is a capability, and I just showed the two fields which we care about: the address and bounds. So the address is references directly to the table of the abstract bytes. And the address is just integer, so you can easily do pointer arithmetics on it. Additionally, memory model keeps the list of the table of the life and quarantine allocations, addressed by unique ID, and they have quarantine flag, starting address, and length. So as you see in this memory model, there is no direct provenance relationship between the pointers and allocations. And in implementation like PNVA AODI, it was kept by maintaining additional fields in the pointers in the semantics, which are not present in the runtime. These ghost fields. So more formally, the memory state of the Cherry C memory model I showed before is shown here. That's the definition we use in COG. So we already looked at the alloc map, allocation, and byte map. Another interesting one is a cap map. Cap map is a table which, for each capability aligned address, it keeps some meta information. The most important is the validity tag. So validity tags for capabilities, they're not stored in the main memory. So when you store the capability in memory, you're storing 128 bits, not 129. And this bit is maintained separately. And this is also how it happens to be implemented in the hardware, like in Morella chip. It's not part of the main addressable memory. It's maintained by the system, and you could not directly manipulate this bit. You can do it through a special instruction. And this bit automatically cleared if the integrity of capability is compromised. So that repeats that. And there's additional couple of fields about the watermarks for allocation IDs and addresses. So the key idea of the PNVI Cherry is that instead of associating additional meta information with pointer objects to track their provenance, it uses runtime capability fields to unambiguously recover their provenance. Getting back to our picture from the previous slides about the relationship between the capabilities and the allocation map on the left, people when usually they talk about the capability, they think provenance, they think that the provenance between the addresses and the allocations. In fact, it's a relation between the pointers and allocations, and the pointer in Cherry is more than that. And it happens that the bounds field is what we can use to calculate this provenance relationship. The idea is, what makes it possible is monotonicity property of Cherry capability derivation. It works in the following way. When you allocate the object first, the allocator returns the capability, which have a bounds matching exactly the footprint of the allocation. And any pointers to this allocation have to be derived from this pointer. You couldn't make them from out of the thin air. You can only derive from this pointer. But the derivation mechanism in Cherry, for security reasons, it only allows you to narrow the bounds of the derived capabilities. You could never extend it. So that means when you're deriving the pointers to allocation from some initial pointer, their bounds will never exceed the bounds of the original allocation. And that's intuition which gives us a way to recover the provenance. So if you have a capability, you have to just look for the lower bound that's sufficient for the matching record in the allocation map, which encloses the lower bound of the capability, and that will give you an ambiguous relation to the allocations. And this will be how you can do the provenance without additional field. There are a couple of other features of PNVA AODI. It's user disambiguation and exposure tracking parts, which are not relevant in Cherry C, and it allowed us to simplify memory model and streamline a lot of it because they're not relevant. Now talking about proofs. Memory in Cherry could only be accessed via capabilities, so you need the capability to access memory. And in memory model, all the capabilities are stored also in the memory. So that means if you define a predicate on the memory state, it could describe the set of memory regions potentially accessible to the program because it have all the capabilities and all the memory it could access. And we express temporal safety guarantee as a memory state invariance that hold for any sequence of memory model invocation. And we defined 3 following invariants. The base invariance always hold. It doesn't restrict memory access. The dirty invariants hold between revocation sweeps and permit access only to live or quarantine memory regions. And the clean invariant permits access only to live memory regions. On the right, you can see the hierarchy of memory regions they give access to. Let's look a little bit on the invariants. This is a base invariant. I don't encourage you to try to read the math on the left. It's mostly for illustration. What it says, what it encodes, is the following guarantees: that allocations do not overlap, all allocations fit within the address space, all capability data in CapMap are pointer-aligned addresses, and next alloc ID and last address are indeed low and high watermark. So it's basically a sanity check, consistency check of the memory state. So it doesn't enforce anything, just makes sure it's reasonable, like allocations do not overlap, obviously. So the next more interesting variant is the dirty memory invariant. So it extends the base one with just one clause. And this clause, it states that for all addresses with a valid tag in capmap, there should be corresponding byte region that decodes its capability. And there must be an allocation, live or quarantined, that includes the lower bound of this capability. Same could be expressed as a security property. Any tagged capability in memory allows access only within the bounds of live of quarantine allocation. The next invariant is a clean in-memory invariant. It extends the dirty invariant with just one additional clause, which states that all allocations are live, by stating that quarantine flag for the allocation have to be false. This is so because when we run the revocation sweep, we discard that allocations after they have been processed by sweep. We remove them from the quarantine as soon as the pointers to them are revoked. So the allocation map only contains live and quarantine allocation. So a security property, that means any tagged capability in memory allows access only within the bounds of live allocations. So we have proven in COG that our memory models preserve the clean invariant, the strictest invariant we defined. How we done it, all the stateful operations in all memory model are defined in mem monad, which is combined state and error monads. And the high-level proof statement are expressed with the help of the logic type class, preserves invariant. I didn't include the full definition here, but the definition says that if we start from the state which satisfies the invariant, the result of stateful operation will either be an error or will result in the state satisfying the invariant. We have proven 36 instances of preserved invariant for high-level operations of the memory model, as well for many auxiliary functions. To aid proof automation, we developed a monadic reasoning framework. More about this in the paper. So to summarize, we developed a cherry C memory model equipped with a sweeping revocation mechanism and the new PNVI cherry provenance tracking scheme. For our model, we have proven the absence of use after reallocate in all memory states and the prevention of use after free in the clean state. The code of our development is reasonable. The memory model itself about 3,400 lines of code with about 4,000 of auxiliary functions, and the proof is 9,500 lines of code. If you want, I encourage you to read the paper, the cherry C memory model for verified temporal safety presented here. Another relevant paper you might want to look at is formal mechanized semantics of cherry C from last year as plus, which discuss a little bit more subtle details about differences between cherry C and ISO C. We talked mostly about capabilities and pointers, but there are some more subtle details like pointer equality and stuff like that. So if you're interested in these details, that's the second paper. If you want to try our semantics, the easiest way is Docker image. So there are two Docker images we have. The first one allows you to run the command lines executable semantics, which is just, you can run small programs and it will give you after either elaboration or it tell you about undefined behavior or execute them. And there's also compiler explorer-based web interface, another Docker container. The semantics is open source. It's on GitHub, Project Cerberus. Test suite is also. My contact information is below, and I'll be glad to answer any questions. Thank you.
Thank you so much. Are there some questions? Anyone?
Perhaps a naive one. So can you explain whether there is a difference what the sweep operation does and a classical garbage collector would do? Are these in principle two names of the same thing, or?
They are similar in the way. So in C language, in general, garbage collector is not part of the standard language, although you can implement it in it. But I think the main difference between the sweep and garbage collector in general is sweep not just release this memory to the allocator to be reused, it also makes sure there is no pointers left to it. So I think that would be the query. Although you theoretically you can implement garbage collector, which also revokes, I guess.
The question over there. Yeah.
So you mentioned there were these, yeah, you mentioned that there were these 4 categories of like use after free and use after revocation, and one of them was allowed. Could you say a little bit more about what, like the thing that wasn't caught?
Yes. I think this diagram on the right is the best illustration to that. Oh, we already know. OK, so we have live objects, and all invariants allow you to access live objects because you need that to your program to work. The difference between use after free and use after revoke is the dirty invariant allows you to access objects in quarantine, and that's use after free. So implication here is a security implication here. You might be able to read some data in the quarantine if you somehow manage to get a pointer to it. So it's not terrible. On the other hand, use after revoke, if you have a pointer to the object, it's have been freed, and then the new object was allocated in the same space, and you still have the pointer to that space, you can go there and read the new object, the data you're not supposed to have access at all. So that's a different security implication. So I think that's the difference. Mm-hmm.
Thanks. So since the revocation sweeps are certainly expensive, maybe they will be unacceptable for some environments. Did you investigate formalization of a system without the temporal safety, but just with the spatial safety?
Yes. So we haven't formulated the formal properties of the of spatial safety, but they will be very easy to express on our memory model, because each capability gives you access only to the bounds which is allowed to. So yes. And one thing I haven't mentioned about the sweeps, there are some very smart hardware mechanisms which make them faster in Cherry. So they mark the pages as dirty, so they run sweeps only for the dirty pages, and there are some other like barriers. It's more on the kind of hardware side I'm not too qualified to talk about, but they're not too bad from performance point of view.
So you said you had these 36 instances of the type class. I was wondering about the relationship to your memory model and to the sort of instructions of the machine. Does that mean also that any program that you have?
So these are methods of the memory model. So in memory model, you have method allocate objects, so you have method write to the memory. And there's 36 methods like that. So for each of them, we proved this invariant.
I see. Thanks. All right, let's thank Vadim again.
Thank you.
I think it's just checking now. try to see if you should just check if the machine works, just to see if there's something. Yes.
Yeah, we have to wait for the more professional people to come. Yes. Maybe just wait for a few minutes.
Yes. All right, we'll just wait a few minutes. Hope that's fine.
Yeah, but I'm muted. Okay. So.
What a shame, I just included all these nice pictures in my slide.
All right, thanks for the effort, everyone. Let's have the final talk here by Katharina Heidler on formalizing the one-way to hiding theorem in Isabelle. Please.
So thanks for staying here. I hope I will give you some intuition. I'm pretty sure that very few of you know what the one-way to hiding theorem is. So I just call the talk as a second title, On the Way to Foundationally Formalizing Quantum Security Proofs. So it's about something about quantum and security proofs. Okay, this is joint work with Dominique Undl from RWTH Aachen. Okay, so let's just talk a bit about what is this quantum security, why do we care, what is it? So probably you will have heard of the latest news from the quantum world where Google announced last December that they have a new quantum computer called Willow. And it's so much better, and it's one step further to having this kind of large-scale quantum computer. But why do we care? So we care, at least in the cryptography world, we care because with large-scale quantum computers, all widely known crypto systems like RSA, Diffie-Hellman would be broken quite easily. So once these kind of large-scale quantum computers exist, we are just messed up. So there's a lot of efforts going into finding new kinds of crypto systems that are also secure against quantum computers. And this is called the post-quantum cryptography or crypto systems. So maybe you've heard of that. So it's a bit about, it goes in this direction. So let's talk a bit more about what quantum computers can do in comparison to classical computers. So probably you know something about that already. Just have a quick overview. So classically you have bits 0 and 1, but and they are embedded in this kind of quantum world as a computational basis, but a quantum computer, or the smallest entity of the quantum computer is the qubit, and this can do more than just having a 0 or 1 stored. It can have some kind of probability distribution on 0 and 1. So we are talking about distributions of states, and they can have some very interesting properties. For example, one very interesting property is this kind of superposition, which is this kind of distribution over several states. For example, so in this case, if you have alpha times one of the base states and beta times the other base state, then you would require, if this is a probability distribution, that alpha squared and beta squared should be equal to 1. And what you can also have, and this is more not entirely correct, like what is stated right here with the entanglement, but what is interesting in quantum computers is also you can have some kind of entanglement between bits, which says that you don't have all the information of distributions in one bit, but it could be somehow connected to something, to another bit. So, for example, there's this kind of entanglement that says if you have that you can entangle two qubits, and whenever you measure one of them, the other one is going to have exactly the same result. So you have some kind of very strange connection going on there. Something else that is notable when talking about this quantum computing is everything is based on this quantum mechanics, and there's a lot of mathematics going on behind there. We are talking about when we calculate stuff or when we model a quantum computer, we're talking about Hilbert spaces and vectors over Hilbert spaces and operators over Hilbert spaces. So it goes very deep into mathematics very quickly. Okay, so this is one part, like the quantum part. Let's talk also about the security proofs part. What is a security proof? It's mostly when you have a crypto system and you want to say it's secure against some attack, for example. There's, for example, the indistinguishability under chosen plaintext attack that you will probably know, which says the adversary can choose two messages and ask you to encrypt one of them, but not knowing which one, and the adversary has to somehow find out which one of the messages it was. So the adversary has to gain some kind of information on the encryption system or on the messages. So overall, quantum security proofs is when we are doing this kind of post-quantum crypto systems classically on our laptops, on our smartphones, wherever. But this should not only be secure when the adversary has powers of huge classical computers, but also has access to quantum computers. So that's the new feature, that these kind of crypto systems should be secure also against attacks using quantum computers. Okay, so what is this one-way to hiding theorem, and where in this huge setting is it placed? So I kind of drew like an overview of what is going on in this whole quantum security world. So of course, in the end, can I see this? No. Okay, never mind. In the end, we of course want some kind of security proofs for concrete crypto systems. For example, there has been released a new standard by the National Institute of Standards and Technology by the US called MLChem, if you know that, based on Kyber. And for example, this is going to be the new standard. We want to show proofs that this is safe and secure to use when attacking with classical and quantum computers. So we want, for example, some security proof for Kyber. Of course, we need a lot of background theory that helps show these proofs. We also need some kind of model of the quantum computer or the quantum adversary. We need to state in these security proofs what can the quantum computer do, How are we modeling it? What can the adversary do? How are we modeling that? And one essential feature of most of these security proofs in cryptography use something called the random oracle model. Maybe you've heard of that already, which is some tool in classical cryptography to somehow handle some reasoning steps in these security proofs. And there's a quantum analogon to that, which is the quantum random oracle model, and that says more or less just, okay, we take a normal classical random oracle model, but we allow quantum access to this kind of classical function. And exactly at this point, that's where the one-way-to-hiding theorem is coming into place. It's talking about how we can we rewrite quantum random oracle models in such a way that we can use these rewriting steps for our security proofs. And then using this one-way-to-hiding theorem, we will formulate these kind of security game steps within the quantum world. And just for you to know, this one-way-to-hiding theorem is used in, I think, most of the security proofs for post-quantum crypto systems. So I know for sure for Kyber, for Saber, for dilithium. So it's like one of the central background theorems that are used. So, of course, we want to somehow know whether all this formal stuff, all this mathematics, very complicated stuff going on is actually correct and the reasoning is sound. So we want to formalize this, and in our case, we want to formalize it in Isabelle. So why? There is something called the QRHL tool, which is developed by Dominique. And this gives us a formal tool to verify and formalize this kind of quantum security proofs. So we have this QRHL tool, which is based on Isabelle. So the background libraries are all in Isabelle. So we have to write all the background theory also in Isabelle. We have to model the quantum computer and the quantum adversary also in Isabelle, and we also have this quantum random oracle model in Isabelle, and we have to model how can we formalize like the access of the adversary to this quantum random oracle model. And what we did in our paper here is that we formalized the one-way-to-hiding theorem in Isabelle and foundationally formalized the proof of this theorem as well. So then the idea would be to show that this formalization of the one-way-to-hiding theorem can then be used in Isabelle for the game steps, and again be integrated in the QRHL tool to completely be sure about all the foundations used in this tool. Okay, so that's what we're going to do. We still don't really know what this one-way-to-hiding theorem is actually about, so I thought about giving you a bit of an intuition of this theorem. So what is the intuitive idea behind it is what I like to call reprogramming. So imagine that you have some kind of function, for example, a function given by the random oracle model or something like that. And in a classical way, you would say, okay, the adversary is allowed a finite number of accesses to this kind of random oracle model function. So he can ask for a finite number of function values. And the reprogramming in a classical way says, okay, if we just change the function values in a very small change set, the adversary most likely will not notice. Why? Because he just can ask for a finite number of points, and if we limit like this number of points, and if we constrain the change set, the probability that the adversary will actually ask for something inside the change set is negligibly small. So this is a central reasoning about how to change this kind of random oracle models classically. And the question that we pose now is, what about the quantum random oracle model? So in the quantum setting, we said, okay, we have superpositions, so we can ask for a probability distribution over states. So what about asking in just one query to the quantum random oracle model for a superposition of all states at once? So you somehow get a probability distribution over all function values at one step only. And the question is, if the adversary is allowed to have some kind of probability distributions over sets, over function values as well, can he detect these changes that we want to make? And if yes, with what probability can he detect that? And that's what the one-way to hiding theorem is all about. It gives a bound on the probability that the adversary can find some kind of information gain from changing a small set in this huge random oracle model. So this is just a theorem statement from the paper by Ambainis, Hamburg, and Unruh called Quantum Security Proofs Using Semi-Classical Oracles from 2018. And that's just the theorem statement. And you have like this left and right probabilities, which say, okay, one oracle, and then we change the oracle, and then we have the right state oracle. And we can, so in the bottom line here, you see that you can bound the difference between the left and right probabilities by some kind of value that is mostly dependent on the change set. So this is a very nice bound because it does not depend on the oracles themselves anymore, but mostly on the change set only. Okay, and this is what we formalize in Isabelle, and it looks like this. Seems quite pretty, but there's a lot of stuff going on behind the scenes. So, for example, you can see in the assumes here already that there's something with trace preserving maps. So we have to really go into the mathematics here about Krauss families. This is Krauss maps, some kind of weird function or operators on Hilbert space operators. So there's really hard mathematics going on behind there. But we could formalize this theorem in Isabelle and all the proofs, which of course are left out here because it would just have taken too much space. Okay, so if we dive a bit deeper into our contribution of the formalization, so what did we do? We foundationally formalized the one-way to hiding theorem. So for example, in this QRHL tool, there is an axiomatization of the one-way to hiding theorem, but there's no proof so far. And as far as I know, there's also no other theorem prover that can handle this kind of formalizations. We did not only formalize, but we also improved the mathematics behind the one-way to hiding theorem. So for example, the proof is split into what is called the pure case and the mixed case state. And so the mixed state is a bit more difficult in the quantum world. And we gave a new and easier proof for this kind of mixed state case. This omitted something called Buer's distance and fidelity of quantum states, which I didn't know about. You probably also don't know about it, and would have taken us months to formalize a whole new library about these concepts in quantum information theory. So we decided, let's just change the proof. And we could find a new proof here. And we also generalized two other things. Firstly, the original proof, or the original statement was only for finite dimensional Hilbert spaces, and we generalized this to infinite dimensional Hilbert spaces. And the second one is, so far we only had terminating adversaries, and now we also are allowed to have non-terminating adversaries. So we also, since we had a very close connection between the proofs, which are also mostly done by Dominique, and we worked a lot together about formalizing. And I asked, okay, I couldn't formalize this part. What is happening here? And Dominique answered, yeah, let's just try and find a different proof. And so there was a lot of collaboration there, which was really nice. And we got some really cool results out of that. Okay, still, every formalization has their own constraints, and our work also has some constraints. So first of all, we have no parallel quantum queries implemented, so every query to the random oracle model is just one query at a time, no parallel queries. And the reason is a bit that the type of the quantum query would depend on the number of parallel queries. So in Isabelle, it's always a bit hard to have this kind of, somehow find a way to formalize this kind of dependent types. There are some methods like tricks, how you can get around these problems, and this would be needed to finally join our work to the formalization done in QRHL tool. So this is really a step that would be needed in the future. I have some ideas about that, how to do it, but I think it's going to take a bit of work. And second, so the probabilities you saw before, like this P left and P right, they actually are dependent on some distributions on the change set and the oracles and another random input. And up to now, these distributions were discrete. And I'm pretty sure that they can also be extended to arbitrary distributions, but that would lead to even more limit arguments and some more, you have to be a bit careful about everything else. So I think this is possible, but it would also take quite some work to do this. So if you're interested in this work, there's a link to our formalization, and we're planning to submit this to the AFP. There's still some dependencies missing, so it's coming. It's only 7,000 lines of code in comparison to other developments. I think this is quite a small development, but the mathematics behind this is really hard. So nevertheless, it's like very densely packed. And this wouldn't have been possible without using several background libraries. So for example, we need quantum registers, probability theory, like in the last talk or the talk before. It was already said that Isabelle has a very great probability theory library. We also need Hilbert spaces, tensor products, Krauss maps, and a lot of mathematical stuff going on. And so many things were already formalized, and without this, this project would never have been possible. Yeah, I think that's about the conclusion. So we formalized the one-way to hiding theorem foundationally in Isabelle, and the next steps would be to find a more concrete bound. So the paper by Ambainis, Hamburg, and Unruh also gives more concrete bounds, but that would involve a new proof. And we would like to have this connection between our formalization and the QRH tool. And obviously, if we could somehow work on our problems, that would also be nice. Thank you.
Thank you much. Right. Do we have any questions?
Thank you. So for the second point of your next steps to incorporate it into the QRHL tool, what do you actually need to do? So what are the concrete steps needed?
So mostly it's this kind of parallel query stuff. That's like the main issue point, that we have to solve this problem. And then I think it's just showing like the equivalence, but that should be quite easy. But like this parallel query stuff is the main issue point.
Any other questions?
Hi, I would be interested, you said that you would allow non-terminating adversaries. So what is actually a non-terminating adversary? I mean, when will he find out the secret?
Yeah, so that's, it's more like a mathematical generalization. But so what I intuitively would think is, okay, for example, if we have these kind of security games like the INCPA game, what happens if the adversary just doesn't answer? Like the adversary is required in the game to, for example, send you 2 messages or send the final bit to you. What if the adversary just doesn't do anything?
All right, let's thank Katarina again. Thank you.
Thank you.
And then remember, now there's the business meeting organized by Nicola and Sandrine.
Yeah, sorry.
Huh.
Okay, so thank you for staying here. So that's almost the end of CPP. So this is where we discussed what happens for CPP this year. First of all, a few statistics about registrations. So you were more than 100 participants to CPP. So you have here the figure for the previous years. So it's a little bit lower than last year, but yeah. Maybe this is because it was here, so, but it's a good number of participants. So I think this is, yeah. Concerning the number of papers that were submitted and accepted, we've got 51 submitted papers, so 1 more than last year, and we accepted 20 papers as last year. So yeah, so which is quite good as well. Yeah. So if we compare to previous years, it's yeah, the rate is very similar. A few words about reviewing. So we had 32 PC members, and Nicola and myself were only chairing the conference, so we didn't review any paper. And the reviewers had 2 months for reviewing and discussing. So we put a lot of effort in discussing with reviewers. So we exchanged, all the reviewers discussed a lot for all the papers. And in the end, if you look at the reviews, so every review was a long review with post-rebuttal comments and so on. So yeah. We also try to have experts for reviewing each paper, so we requested 26 external reviewers. A few statistics about the proof assistance used in the submitted and accepted papers. So compared to last year, we had more Isabelle submissions and more ROC submissions. So we had 26 ROC submissions and 10 Isabelle submissions. So we had a little less submission for Agda and Lynn, and yeah. I don't know if we can conclude something from these figures because these are only small numbers of submissions. And yeah, you can also see the differences between submitted and accepted papers. So yeah. Now we would like to talk about the Distinguished Paper Awards. So for CPP, like in other ACM SIGPlan conference, so there is a rule that around 10% of the accepted papers will be designated as distinguished papers. So this year, so what is a distinguished paper? So it's a paper that for which the program committee thinks it should be read by a broad audience due to its relevance, originality, significance, and clarity. So this year we had 3 distinguished papers. I don't know if there are people online because yeah, the first distinguished paper is awarded to a remote presentation. So I know, no one is online? Okay. So yeah, actually, maybe they already have received the award that I sent them before coming here. So it was for the paper certifying rings of integers in number fields, and it was presented by Alain, who was online. Then we have another paper that we saw, split decision, explicit context for substructural languages. So it was presented by Daniel Zacon. I don't know if Daniel is here. Or, okay, so maybe you could come to receive the award. So congratulations again. And then there is a third distinguished paper, which was the next-gen modality. We saw today a modality for non-frame preserving updates in separation logic, and it was presented by Aina. And yeah, so congratulations again. Okay, so I will take this opportunity to thank all the PC members who put a lot of, who did a lot of work reviewing all the paper and discussing a lot during all the evaluation period. So here are the list of all these people. Maybe we could thank them, I think, yeah. And among these PC members, so there is one amazing reviewer. This year, the Amazing Reviewer Awards goes to Carl Pamslock, who unfortunately could not come here today, so he's in Europe, in Sweden. So yeah, let's thank him, even if he's not there. Okay, we would also like to thank all the external reviewers that you can see here. Yeah.
Hopefully there will be maybe PC members.
Yeah, maybe, maybe this will, yeah. We would like also to thank all the POPL organizer and the CPP steering committee who helped us setting all these conferences and all the logistic details and so on, and all we had to know to make work this conference. We would like to thank as well the student volunteer who helped us during the conference, and the AV team as well. And then a last big thank you to all the authors and all the participants. And also a big thank you to the 3 sponsors we had for CPP as well. So that's the end of CPP. I don't know if you have questions, if there are subjects you would like to discuss or something you would like to say about this conference, the way it was organized.
Maybe you can discuss about next CPP.
Yeah. And maybe you can think of questions and yeah. So a few words about CPP next year. Of course, it will be co-located with POPL'. Nicolas will be the co-chair with Nikhil Swani. And Catherine will still be conference chair, and we will have a new co-conference chair who is Yannick Zakowski, who could not be here today as well. So good luck with CPP next year.
It will be in Rennes, for those who don't know. No. I say nothing.
Okay. So
it's to get more participants next time.
Okay. Okay. So yeah, maybe if you have questions or if you want to discuss something, yeah. So if you want to know more about POPL' next year, you should come to the POPL' business meeting on Thursday evening. Yeah. And you can also send us feedback for this year by email. Yeah, if you are too tired to discuss.
Also, if you have feedback about the call for paper, or we try to change it a bit this year.
Yeah.
So if you like the improvement, or if you have other suggestions, we could impact them for next year. But you could just send me an email.
So maybe we could thank Nicolas and Sandrine.
And for those who don't know, there is a Jane Street thing. I think it's kind of almost now. At 6, yeah. I don't know exactly where it is, if it has been changed because of the flood or not. Yeah. It's downstairs, second floor? Okay.
Okay.
So see you there for those who go.
So yeah, at the end, bye.